Good morning, everyone. For those joining on the live stream, welcome to Stream 2. And for those joining us in person, I hope you had a good morning so far. Before we begin, some housekeeping and quick reminders. We're using a tool called Slido for you to ask your questions during the sessions. To access Slido, you can scan the QR code. Okay. Or use the event ID. I'll read it out now. It's 4025-787. For those joining us in person, if you're feeling the room is a bit full, there's also an overflow room where it's being streamed. And I think that's it. We can kick off the session. So let's welcome first Clara Fabiola Oliva, Vice President of Data Analytics, AI, and Customer Insight, and also welcome Nicola Visioli, Strategy and Data Analyst. They're coming to the floor to discuss team's journey to find the why behind customer behavior, find optimal interventions, and shape a data-driven future. Welcome, Clara and Nicola.
So, hello everyone. So thank you very much for being here, for the opportunity, and for this event. So I'm Clara Oliva. I'm Vice President for Data Analytics, Artificial Intelligence, and Customer Insight in TIM, and I'm a board member of Olivetti. TIM, I don't know if you know the company, is one of the biggest and also the historical telco company in Italy. And of course, as a big company, you can imagine how difficult is a transformation. And data transformation is a very difficult, a very big challenge for TIM. So I'm the responsible for choosing new technologies, of course, and artificial intelligence, tool set in order to support, both internal and external market purposes. Of course, artificial intelligence and data analytics are, the core to make the right decisions. And on one side, to create efficiency on operational process, and on the other side, to create new growth opportunity. It means that, of course, we need to understand better our customers, to talk with them in a different way, and to create new stream opportunities. But as I was saying, TIM has a very big story, and of course, transformation is a challenge. So the first thing that we had to work on was data strategy. So here in the slides, you can see some of the few core elements that were the starting point for us, of course, to make this difference. And we can start, of course, from the data framework, the data architecture. So having new technology and new tool set, so having the opportunity to work in a new, environment, technological environment, of course, is one of the first steps that we need to do. And we started to do it, of course. Then data governance. So I know that it's very boring stuff, and it's made of data quality, data catalog, and so on. But, garbage in, garbage out. So the first thing that we need to do is to collect the right input data, to work on that, to work on quality, to work on processes. And here is the new, phase, because once that you have the right architecture, you have the right tool set, and you have the right information, the right data, of course, you need to start on process, organization, skills. So, again, big company challenge. We need to work on a data culture. We need to work on a different way of working and a different way of addressing our problems. And, of course, risk management. So, European Artificial Act, it's one of the new challenge for everyone. So we need to work, on the risk, addressing all the problems that artificial intelligence system and tools can create. So this is the first, let's say, layer. But starting from there, so we did a lot of work. So I have a team of 60 people working with me. They are data analysts, data scientists, machine learning engineers, artificial intelligence translators. It means, of course, that we need to support business units. And to do it, we need to create empowerment. We need to create this data culture. So we work on the day-by-day working. So it means that we created, here is just few, let's say, AI models that we were working on. But of course, it means that we need to support and to help them, even if it is a dashboard, let's say, it's important to help everyone to work on this side. And of course, what is important is the ambition. So the ambition, as I was saying, if we need to work on a data-centric environment, we need to understand and to empower AI systems, and also causal reasoning is one, of course, of this. And we need to work on better understand our customers. So the scope is, of course, customer care, marketing, and sales. So generating new, let's say, new contents and new personalized services. But on the other side, process automation, so efficiency is one of the main steps that we need to do. And also of course, all the CapEx optimization. As I was saying, causal reasoning is the target for us to understand better what we are doing and to make the right decision. And here is exactly what Nicola will explain to you. I will leave the floor to him, because of course, for us, decision is already part of our ecosystem. Thanks.
Good morning, everybody, and thank you, Clara, for your presentation, your introduction. So, in this session, I will try to sorry. As Clara said, I'm data scientist that now I'm working on this on our group. So I will try to explain to you our work on developing a causal inference framework that try to reduce customer churn in telecom industry. So during this session, I will try to walk you through our method, our strategy, and the valuable insights we gained combining causaLens decision-OS platform with our in-house causal inference platform and applications. So, as you know, telecom industry is a very competitive and saturated market. This is true, especially for Italy, where there are a lot of operators and where the customer prices are the lowest in Europe. So we understand that the cost of acquiring a new customer in this situation is much higher than retaining existing one. This is why we felt the need to understand what the behavior of our customer. Of course, so the question is, can we leverage on a non-core team service, in this case a TV service, to try to enhance customer retention and so reduce churn? As Clara said, in team we have been using machine learning models and also more complex deep learning models to try to predict churn. As you can see from some of the metrics I reported in this slide, results are good but not optimal. Moreover, as you know, those machine learning models are inherently predictive. They can tell us who is likely to churn, but not why. Additionally, if you want to take some retention actions, for example, sending emails or discounts or offers, we eventually disrupt the patterns that those models have learned. So they became even more ineffective. So we felt the need to switch from mere prediction to understanding causality and to try to estimate the real effect of our actions to take better decisions. So this study is focused on team-fixed database that team-fixed clients that give consent to profiling. The dataset comprises over 3.3 million of instances we observed in one single month and more than 4,000 variables. So the richness of this dataset, of course, allowed us to delve deeper into better understanding customer behavior. But of course, it presented the challenge of dealing with a great search space. To overcome this issue, we used the solution proposed by causaLens Decision S that aims to recursively merging pair of cluster of future. And it's essentially a hierarchical clustering based on variables greater than instances, and we got some good results. However, to have a better understanding of the cluster we are analyzing, we use a large language model to create a few clusters based on future description generated directly by the large language model. As you can see, I reported some of the prompt we use. Particularly, we use a LangChain library in Python to query the large language model. But also, we asked to the large language model to help us to identify some prior knowledge to put in the causal graph to obtain a more meaningful causal graph. As in this case, I reported some of the prompts. In particular, we asked to the large language model to identify clusters that are likely to be dependent from many other clusters, but we move further, asking to identify direct causal relationship between clusters. Of course, being a sector expert, we were able to modify some suggestions, but in general, we found them quite accurate. So, as I said, we use this prior knowledge to run in Decision S causaLens some causal discovery algorithms. In particular, we run PC, FCI, and Lingham algorithms. And finally, we choose the graph that better fits our expectations and eventually modifying manually some edges. So to evaluate this graph, this final graph, we use some independence tests. In particular, we test how many graphs obtained permuting the original nodes lie in the same Markov equivalence class than the original DAG. And since we found that our DAG is characteristic, is informative, we perform another test which aims to verify how many DAG permutations having as few or fewer local Markov condition violation than our DAG. As you can see, the graph we got from PC algorithm in this case has exceeded both of those tests, and so we don't reject the DAG. So the next step was to associate to the causal graph a structural causal model, assigning to each no-root node a functional form that can be, for example, an additive model of parents and observed noise. So in that way, we're able to perform a future relevance analysis that aims to identify which parent node has the greatest impact on the target variable. But more importantly, we are able to perform an intrinsic causal influence method that estimates the newly added information by a node in the causal path that was not inherited by parents. As you can see from this last model, some of the variance of the target variable remains unexplained. This can be due to some model inaccuracies, or maybe we don't consider all the relevant variables in our model, or maybe when we decide to use cluster instead of original variable, we lost some information. Anyway, results that we got are not trivial. Indeed, as you can see, our variable that we have chosen a priori as our possible treatment, that is our non-core TV offer, is indeed one of the most important in explaining target variable. So in this case, it's safe to also switch from a model-based to a design-based identification. That is, we can also try to estimate the average treatment effect of this variable of our treatment, even without relying anymore on the functional form of the structural causal model if we don't believe completely on them. What we need in this case is to deconfound the data. That is, indeed, we applied the 4 different causal inference methods to obtain the average treatment effect. All the methods, you see, agree on the same value that is, of course, much smaller than the one that we got with a naive estimation, that is computing a difference in means. But there is something that we are expecting, since now we are controlling for co-founders, and so we are eliminating their bias. But more interestingly, this causal approach gives us the possibility to identify clients that, or group of clients that we want to prioritize. Indeed, we use some the machine learning models like causal forest or other double machine learning models or double robust estimator to calculate the conditional average treatment effect. We use also some validation tests like a Gini curve and other uplift curve, RS curve, to select the best estimator for our data, in this case, the double robust estimator. At this point, we just need to fix a threshold value, or if we don't want to care about outliers, to select an interval to retrieve all the customers that are most likely to be affected by our treatment. And so we can focus only on them. Moreover, using always the same double robust estimator and some statistical tests, we were able to verify that a lot of those customers are indeed the oldest one in our database. So it's a result that quite surprised us, but it's very important because now we can easily access to them. So to sum up, combining causaLens decision S with our framework, causal inference framework, and also using some large language model causal capabilities, we were able to optimize the resources because now we can focus only on more sensitive clients, so we can save money and time. And of course, we can also maximize the impact, since now we can be pretty sure that unlike using machine learning models, predictive models, we are able to enhance customer retention. Finally, in this slide, I want to show you some other possible application of this framework that can be used in telecom industry. For example, we can select a variable that we need to target to upsell new services, or maybe select variable, identify variable that we need to consider if we want to reduce customer complaints, or even to find features that are the most related to customer patterns, so we can generate value through data monetization. And thank you for your attention.
Amazing. Thank you very much. We do have a couple of questions. We also have a couple of minutes, so hopefully we can get some answers for you. First question, do you run into situations of cyclic graphs, i.e. non-DAGs? How do you and Causal AI deal with these situations?
Yes, yes, there are sometimes we got some non-DAG graphs. Yes, we can, in causaLens, the decision S, there is the possibility to choose the part of the graph that is not a DAG using a scorer. But we can also, for example, also we can choose, we can examine also the graph and deciding with if the customer, if the user has a good knowledge of the problem to decide to delete some edges and so to select the part of the graph that, of course, to have a DAG. And so, but of course, causaLens has a scorer that can help us to decide which part of the DAG we have to consider, and so we can only work on this part of the graph.
One final question. How much uplift do you think you can get from using LLMs in causal discovery?
Yes, of course, we are, as I said, sector experts. So maybe we were also able to build the cluster we use alone. But first of all, we have a lot of variables, in this case, more than 4,000 variables. So the LLM, first of all, help us to reduce the search space, because also manually selecting all the variables to create a cluster is a big deal. But of course, using a large language model, we can speed up the process, and then eventually we can modify what the LLM suggests to us. But in general, as I said, the LLM gave us a very good solution in building clusters, and so, and also prior knowledge to put in the causal discovery algorithms.
Amazing. Thank you very much.
Thank you, Clara and Nicola. Now we're shifting focus to the world of finance. Please welcome Alvaro Ibrahim Rodriguez, expert data scientist at BBVA. He'll be discussing causality in retail banking at BBVA AI Factory. Please remember to use Slido for your questions, and welcome.
So good morning, everyone. I am Alvaro Ibrahim, and I'm a data scientist at the AI Factory of BBVA. And actually, I'm doing this talk on behalf of my colleague, Jesus Renero, who unfortunately couldn't come today. So maybe I don't have the answers to all of your questions, but I promise that I'll do my best. Today I'm very excited to share with you how Causality is revolutionizing retail banking at BBVA. And for those of you who don't know, BBVA is one of the most or the biggest banks in Europe and Latin America. It operates in more than 25 countries, covering a wide range of financial services. And for a few years now, it has bet heavily on AI to enhance its core operations. And that's why it created the BBVA Factory, which is our AI hub. This hub is distributed across 3 countries, namely Spain, Mexico, and Turkey. And it is composed of multidisciplinary teams comprised of ML engineers, data engineers, AI architects, product experts, and of course, data scientists. These teams collaborate to create end-to-end data products that are used to solve business needs at BBVA. And one core distinction of these teams is that they have a strong focus in innovation. Some examples of these are, for example, some prototyping programs, which are called the X programs, and also quick study initiatives that try to figure out how to include state-of-the-art or cutting-edge methods into our models and our products in order to further improve them. So what do we actually do? Our work revolves around 3 pillars. The first one being that we want to ease the interactions our customers have with us by using AI as much as we can. The second is that we always try to use the most recent stuff, state-of-the-art methods, in order to improve the core bank and the core processes of the bank, like, for example, fraud detection or risk management. And lastly, we work for enhancing the relationship with our customers by providing them personalized experiences. So why causality it is important to us? Well, in most of our cases, we can just simply run A/B testing or randomized exploration. This is due to regulatory restrictions, technical inviolabilities, and even ethical concerns sometimes. Without those tools, causality comes as a very handy tool for us because it allows us to further understanding our models and also evaluate the effects of certain actions. And often all of this only with observational data, which allows us to draw far complex relationships between variables and thus making far better decisions. So today I wanted to share with you 4 use cases that currently are applying causality at BBVA. And within the bank, there are several initiatives, or within the iFactory, which are working with different business lines across the bank. Here are 4 of them. The first one being financial health, which is an initiative that tries to build tools that enhance the finances of our customers. For example, giving them advice on what to do with their savings, alerting them when anomalies happen, or forecasting, for example, expected movements. So the question here was to evaluate or get to know whether these tools are really useful to our customers and to what extent. The second one is the personalization program, which tries to hyper-personalize our digital channels to its customer. For example, personalizing the view of the app depending on the profile of the customer, or recommending them several financial products. The question here was regarding to whether recommending or showing a client an ad of some of our products really makes them more prone to acquiring them. The third one is risks. As you already know, we're a bank, and at the end of the day, we lend money to people and companies. And sometimes, this line tries to make tools in order to further minimize potential losses. So sometimes clients default, and we want to give them some tools in order to solve their debt problem. So in some very special scenarios, when the debt status goes really bad, the bank is willing to accept partial losses in order to avoid further potential losses of the entirety of the debt. So the question here, and it is a very particular and special question, is how much are we willing to lose in order to avoid further potential greater losses? And the last one is dynamic pricing, which is a program that builds algorithms to intelligently price some of our products. And today I'll be covering a very specific case of one product, which is our pre-graded loans. So for the financial health case, there are, if you recall, we tried to offer our clients tools for improving their finances. So here there are several problems or issues. The first one being that defining what is actually a healthy financial situation, it's not trivial. We can use proxies like, for example, total debt or satisfaction scores. The problem with them is that they often exhibit high variance. So that's the first problem. And the second is that these tools for the bank have been existing for years now, so it's currently impossible to isolate a control group. That is where that's why we tried to apply causality. The idea was to compare the total savings amounts of users of these apps versus non-users of these apps. The problem is that here there is an inherent bias. So we applied techniques such as PSM or double ML while adding correcting confounders like age, expenses, navigation features, etc., in order to correct those biases. And the results were pretty good, as you can see. We actually found a positive effect for our Spanish and Mexican users of their savings being incremented by 11% in Spain and 20% in Mexico, which is great. Regarding personalization, here we wanted to answer actually two questions. The first one being, is a client more likely to purchase a certain product once we show it to him? And the second is that we wanted to compare two versions of our recommender system. We had a previous baseline and we have the latest version of our system. Here we have countless issues. We try to apply A/B testing. However, there are too many types of biases that damage the results. For example, we have selection biases because heavy users of the app are more likely to be treated than non-heavy users. We have attribution difficulties because lots of the products take weeks, if not months, to become purchased. So making the attribution of a conversion through a show of an ad months before, it's quite difficult, and we often find that we don't have the exclusivity of impacting the clients. There are other channels that also show ads to our clients, and that's very difficult to control for. So in order to solve this problem, we mainly applied meta-learners to study these effects, and the results were good, as we found that there was indeed positive effect to both of the questions. So that's allowed us to validate our hypotheses and models. And as a byproduct of that, we also identified a certain subset of clients that weren't very sensitive to our ads. And that's meaning that if a client was very prone to a certain product, showing them didn't matter because he was going to purchase it anyway. So we could use that space on the app to show other things. Regarding risks, if you recall, we want to answer the question of how much are we willing to lose in order to minimize future potential losses. And I must remark that this specific use case comes only from a pure research perspective, and it is not in production right now. And as a matter of fact, if this problem interests you, later this evening, my colleagues Clara Higuera and Javier Moral are covering this in more detail. So I strongly recommend you to attend their session. So there are, returning to the matter of this problem, here there is a quite important restriction, that is that we cannot do random exploration because we cannot offer or make different offers to similar clients. So that only leaves us with historical data or observational data, which is very scarce and presents, again, quite considerable amount of biases. One, for example, is selection bias, since historically similar clients were offered a similar percentage of condonation. So we have to follow a rigorous debiasing process, and with that we managed to learn a causal graph and train train a niche learner to do causal inference in order to produce counterfactual estimates for new clients. So this is an example of something that wasn't previously possible and causal inference enabled. Lastly, regarding the dynamic pricing program, if you recall, we wanted to focus on the question of how much can we lower the prices of our pre-granted loans in order to drive demand up while avoiding losing revenue. So here, after applying several devices and techniques, we were able to model the demand curve for a given price and a given risk score using those two models, the Probit and the Tobit one. And the results were also very positive, as we could drive our prices down, stimulating demand and also increasing our revenue. So as a summary, Causality is a very important tool that helps us not only understanding what is happening, but more importantly, why it's happening. And it offers several benefits for financial institutions or banks. I have put 4 of them here, which in my opinion are the most important ones. The first one being that in a heavily regulated industry like ours, it is crucial to meet legal standards and sometimes even go beyond them. So knowing the effects of our actions makes us able to move faster while staying compliant. The second one being that every day customers want more and more personalized experiences. So if we can estimate the effect of doing certain actions, we can drive the responses of the clients, and we can further tailor more personalized experiences to them. The third one is, as I mentioned before, having the ability to estimate the effects of our actions makes us able to plan with a further viewpoint. And that are the examples of the risk and dynamic pricing, which, as you know, allowed us to maximize long-term goals of minimizing total losses and maximizing revenue. And lastly, as I said, we often cannot do random exploration, so it becomes a very useful tool in order to estimate the effect of our hypothesis and our models. And recall that in the 4 previous examples, only one of them used A/B testing, and even with that, it was not enough. So what's the future for us? Embracing causality, it's not just a technical issue, it's a cultural change. And it has certainly added a more scientific point of view to our decision-making processes. Innovation is one of our core missions, so we are still studying what more cases could benefit from causality. And with the bloom of Gen AI technology, more and more use cases within the bank arise every day. So we are already exploring the intersection of these two fields with the aim of finding causal relationships between large amounts of unstructured data. We also see causality playing a critical role in regulation because it allows us to further understand the impacts of automated decision making. And as for the future, BBVA will, we are going to push forward the causal mindset within the organization and include it in more and more of our use cases. So thank you very much for your attention.
Amazing. Thank you very much. We do have a lot of questions, Alvaro,
Wow.
but we don't have a lot of time.
Okay.
So I'll do the top two, and then feel free to grab Alvaro wherever you see him lurking around the building. First question is, in your personalization case, is causal AI making the bias risk more likely? Maybe using sensitive features like gender, faith, political views, etc.
We actually, in most of our use cases, cannot use sensitive information such as gender, sex, or so. We're mainly using navigational features and also features like balances or everything that describes the behavior of the customer in a financial way. Regarding this question, those features don't matter.
Amazing. Final question. How do you determine which estimates are better when there's no ground truth?
Well, we depending on the case, we usually rely on domain expertise for some cases. In other, we apply several evaluation techniques like gain curves or the evaluation of the counterfactuals we get.
Amazing. Thank you very much, Alvaro.
Thank you, Alvaro. We'll now take a 30-minute coffee break. Please be back in your seats by 11:45 for our next session. If you come back and this room is full, there's also the breakout rooms also on this floor that have a live stream of the session. It's an excellent opportunity to network and try out demos and chat with our speakers and our team. If you're joining a workshop, it's right outside in the council room. And enjoy your break. I'll see you in a half hour.
do I
Okay, welcome back, everyone. Our next speaker is Alexander Giannara, data scientist. Oh, sorry. Did I say it right?
Yes.
Okay.
Alex would have sufficed.
Oh, okay, I see. He's a data scientist at Bookprint. Alex will discuss the technical hurdles and solutions in implementing causal modeling at Bookprint. Also remember to head to slido.com to ask your questions. The event ID is on the slide. And welcome, Alex.
Thank you. So, hi and welcome everybody. Also from my side, I'm very glad to be here. I think some of you might have heard Chris's talk earlier this morning, who talked a bit more about the business side of this project. I will talk more on some of the practical lessons from the data science perspective on how we implemented this project, and basically try to give you some key takeaways along the journey if you want to do something similar, some of the things we learned. As Chris mentioned, we call this project Decoding E-commerce because essentially we are trying to build structural causal models, or one structural causal model to solve a specific use case, namely business steering. And for those of you who were not there, who is our company, or who are we? We are a online e-commerce retailer specializing in the outdoor space. So we sell outdoor apparel and outdoor gear. We are active throughout Europe. And basically, again, we have these very two basic operational levers, namely marketing strategy and pricing strategy, that we try to balance on a weekly strategic basis to optimally steer our business. And the business question that this project and this use case is trying to tackle is basically, well, the business came to us and said, well, if we change our weekly marketing or pricing targets that we set on an organizational level each week to some specific value, to some specific strategy, how does that affect our final outcome, so our demand sales, so how much product we sell on to the demand that exists in the market. And from that, I think Chris mentioned it this morning, basically, they ask this question, which is a very causal question, because we know that if we change our targets internally and our business then in the operational processes acts according to these targets, that really has a huge impact on our operating margin and our profit in the end. So this is a super interesting question and a very important question for our business. The challenge basically that we are facing to answer this use case is how can the business understand the causal impact of these operational decisions on the business performance? And this is again, I want to really reiterate this is a causal question, right? We're not just interested in making a forecast of our demand sales. We're actually interested in if we change something strategically, how does that affect our final outcome? So what have we done in this project? Well, as Chris mentioned, we basically try to identify the causal pathways, try to set up a structural causal model that help us understand the pathways from business decisions to business outcomes. And then secondly, we obviously want to model and quantify those relationships to get some estimates and then sort of run in the next step optimization questions and also to be able to implement scenarios and ask interventional questions. Generally, I would say we had two goals. The first one was to help the business stakeholders understand the impact of their operational decisions. And the second one, and this is the one which really you've seen, if you've seen Chris' talk, is build a tool where the business user in their weekly operations meetings can say, hey, what happens if I run an intervention? I want to set this specific goal. I want to set this specific goal. These are the numbers we're expecting for next week. These are the targets that we want to hit. And what is the causal impact of that throughout some of the key KPIs that we observe in the business and our final KPI, the demand sales that we make. A brief interlude. So what is this talk? It is very applied. I will not talk deeply about algorithms used or estimation techniques. I will more sort of give you a more process-oriented talk and expose some of the challenges that we have faced, sketch some of the solutions that we have found, just inspire you hopefully to give you some ideas on how, if you want to do something similar, you might approach some of these targets or questions. Also, as Chris mentioned, we still have some open things. We are still working on this model. We are further trying to improve the model, and there are some things that we want to improve on as well. So the first step, if you think about the pipeline from basically this business question onto the final product, namely the tool that you see when the business user sits in this meeting and sets their specific targets, is the first step is building a DAG, right? So building the direct acyclical graph that represents the information, that represents the causal flow throughout these different variables that you're interested in. And from a data science perspective, this is a very challenging task and something that is often looked over when we read about specific use cases, namely how do we actually get from domain knowledge to a DAG, right? If we just read documentations, we often have these ideal typical settings where the data either stems from a data generating process that we have implemented ourselves to sort of model stuff and learn about the TED tools. But as we all know, as data scientists, the real world often is very messy and domain knowledge often is very obscure, is not really easily captured in the business, or sometimes doesn't exist, or sometimes it's just in very different places. So what we have basically done, and I think this is something that I really want to drive home, if you want to build a structural causal model, then I think you need to start from the domain knowledge. And often as a data scientist, this is not your domain of expertise, right? You are not an expert in, let's say, business steering. You're not an expert in pricing. You're not an expert in demands, right? Whatever marketing models. But you probably have someone in your business who is. And sometimes you sit then there in these meetings where you try to understand the process that you're trying to model, try to build a DAG, and you're just sitting there basically like, what the hell is going on? What am I even listening to here? I don't understand anything. Now I'm discussing about the fifth KPI that basically just means the same thing. And I want to tell you, these are the important meetings. Even though sometimes you really feel like your head is going to explode, everything you hear in these meetings and the domain knowledge really is the foundation of the DAG. And it basically encapsulates all the key critical assumptions that you build your structural causal model on. And if you don't follow through with these assumptions, don't listen to the process, then maybe if you have the wrong assumptions in your DAG, what model are you actually building, right? Is it a useful model? Is it actually a causal model? Or are you just fitting to some other stuff? So for me, and for us, this was a very long process. It was a very iterative process where we listened to the domain experts, built the graph, tested the assumptions, so ran some conditional independence tests, did some EDA, did some visualizations for the business key stakeholders, and then reiterated. And this is a process that takes time. So don't expect fast results. Sometimes you can get them if the process is very small and you're an expert in the process. Otherwise, it might take a while. Another thing that we found super useful was after we had built our initial graph based on domain knowledge, we ran additional causal discovery. And for us, the perspective on causal discovery in that setting was causal discovery is super helpful to generate hypotheses about the underlying graph. It does not tell you necessarily the truth, right? It suggests something. It suggests adding an edge. It suggests dropping an edge. It suggests there might be some unobserved confounders in there. There might be some missing connections. But it never tells you anything about the real world. It suggests you a hypothesis. And I think this is where the science part in data science comes in, right? If the model suggests something, if the algorithm suggests something, you are the scientist that needs to take that as a hypothesis, question the assumptions, and then either accept it or talk to the business and say, hey, what do you think about this? So again, for us, the key takeaway for building these structural causal models is that domain knowledge really is pivotal, because this encapsulates all the assumptions that you really need to make about your model. Secondly, and this is something that we have done as well, is we ran multiple causal discovery algorithms. We compared them. All of them might generate slightly different outputs. In the slide up, I said we ran multiple oracles on these discovery algorithms and compare them, right? Take the input as hypotheses, go back and iterate. And this really, again, is something that is not really talked a lot about, but I think this is something that we really should be aware of, and this is something that people should know. Quick shout out to this FCI tiers algorithm. If you don't know the paper, it's an amazing algorithm for causal discovery, because it allows you to structure knowledge into different tiers, and this allows you to integrate domain knowledge into the causal discovery algorithm. All right. Then we come to the next step. And the next step, obviously, then is model building and estimation. And here, now I want to talk about two specific points that we faced. And the first one is, how do we deal with time, right? Chris talked about the fact that we have time series data, right? The business makes decision on day T0, and over the next 6 days, these effects materialize throughout the decisions of the company. We basically embraced non-stationarity. We said we can't get rid of it, right? It's there, it exists. This is the data that we have. This is what we're trying to model. But still, we didn't want to run like a full time series causal graph, but we took out some of the components of a full time series model, where we said, okay, first of all, our business, we know, works on these weekly periods. So we use 7-day rolling windows to actually both train, but then also because this is the period of time that we're actually interested in our final application of the model. Another point that we really want to make is that we use 7-day lags to address some of the temporal spillover effects. What do we mean by that? If you listen to Chris's talk, he basically said, if we make a decision on our marketing strategy, then this translates operationally into some changes into our marketing department, and that translates into changes on the Google bidding algorithm, right? And the Google bidding algorithm is not our best friend, so it does not necessarily work in the second that we tell it to change something. It needs to learn and it needs to adapt. So we necessarily, if you change something in 1 week, this will have spillover effects, temporal causal spillover effects into the next week. And we need to address that, right? So think about these temporal spillovers, maybe build in some lag variables into these structural causal models to address these specific questions. Furthermore, we used some lag variables to proxy for certain market conditions where we knew that we might not have actual data on some of the underlying causal mechanisms, but we could generate some proxies by using some lag variables. Finally, Chris talked a lot about the weather. We know in our data we are very weather dependent. Weather is very seasonal, right? So again, we embrace non-stationarity and say, okay, now we use exogenous variables that we know capture some of that seasonality, capture some of the time trends, and try to bring them into the model that to actually sort of deal with that. A final point, how we deal with time, and I think this is something that I also want to mention, we retrain and validate our model weekly. And why is this important? Well, I think this is important because obviously there might be some data drift in how the underlying structural parameters are estimated and actually also exist in the real world, right? It might be that sometimes causality slightly changes over time in the underlying data generating process, and thus it makes sense when you re-estimate the model to also take a look into, okay, what are the estimates, how are the estimates changing of these different parameters, and what are the model test statistics, how do they evolve over time? Because if you don't retrain the model, then you will have data drift, and then you might run into issues where the causal mechanisms that you're trying to model are not the same 1 year in the future. Another suggestion I want to make, and we really talked a lot about this as well, when we talk about these structural causal models, you have to make functional form assumptions about both edge activation and aggregation functions. So basically the functional form of the condition, the dependence between x and y, but also on how different nodes then flow into one specific target. And here, we want to really encourage you to also think about the data generating process. Not just let the data speak, but also think about, okay, if the relationship between x and y from the business, from the domain knowledge, from the domain experts, we know there are diminishing returns, right? Then maybe it makes sense to sort of restrict the functional form to that setting. Why is that important? Well, it is important because if you think about, let's say, the distribution of the data on the specific node that you're trying to model into a target, if you don't have if the density is not uniform, right, but you have tails, then obviously in the tails towards the limits of the range, you will not have a lot of data. And if you implement a, let's say, a linear functional form, then that might fit well given your data. But actually, that is only true because you have very limited data in the tails and you extrapolate via the functional form assumption from the structural causal model. So it also makes sense to keep that in mind when building the structural causal model. Again, go back to the domain experts and think about, okay, what are the assumptions, the underlying assumptions about the data generating process that I'm trying to bake into that model. So the key takeaways for us are basically embrace non-stationarity if it exists, deal with it in any way, shape, and form you can. It might not be perfect, but at least don't ignore it. And again, we are very open to discussing that there are still some problems, and we still want to see whether there's some more. Finally, do not overchase predictive accuracy and rather take into account the domain expertise. All right, one final thing I want to briefly mention, and this is about interventions and nowcasting. We have talked about our structural causal model, but now the business came to us and said, hey, we have this one target, but we have a second target that we're interested in. What do we do now? We don't necessarily want to build a full structural causal model for these two new KPIs that the business now wants to bring into the structural causal model because they're interested in this new outcome. What have we done? Well, we decided to build two nowcasting models that we train on the same data that we use to train the structural causal model using the machine learning technique of choice that you want. But then, actually, when we apply that model in production, we can use the post-intervention outcomes of the structural causal model, pipe that into the machine learning algorithm to then get somewhat predicted outcomes of the target that we're interested in without having to build a full structural causal model for that specific target. Why is that important? Sometimes it's just not feasible, or you don't want to necessarily build this full structural causal model for some target. It might not be feasible, you might not want to do it, it might expand the scope of the project to some ginormous amount, but you still want to give the business user some insight. And then we really found this combination of machine learning prediction methods as a setup as a nowcasting model with the structural causal model to be super informative. I think the important part here is make it transparent to the business that this specific part might not necessarily be fully causal, right? So sort of make it sure that the business understands we have this one target and the additional supplementary targets that we're adding, the figures might be quite accurate, but they are based on a prediction and not on causality. And this is something that I think is the bit of the, you might not want to do it, but you probably can do it, hang up here, because getting that message across to business stakeholders sometimes can be very tricky. But again, it is very, very helpful if you need to do that. And we found it quite accurate, actually. I think you have seen this slide with Chris as well. Basically, then we want to productionize this tool, right, where we have a tool where the business users in their weekly operations meetings can set their expectations, can set their operational decisions, and that allows us run their interventions to then get a demand sales forecast or a nowcast or whatever for the next week from the structural causal model, and we can investigate along the different causal paths how does that affect certain downstream KPIs within the causal path, which is super helpful. So as a final summary, I think what have we learned? Well, we have learned that causal modeling techniques, specifically structural causal models, can integrate domain and process expertise with robust data modeling. And this is something that is super cool if you want to solve such a use case. We have also found that this nowcasting method really works very well as a supplementary add-on, but again, messaging towards the business is key here to keep expectations in check and not confuse the two. I think I hammered a lot on the sessions with the domain experts, but I think for the causal interpretations of the model that you're building, specifically if you're building a structural causal model, the assumptions in the causal graph are really pivotal. So this encapsulates the entire assumptions. So really spend time on building the DAG. Another method I want to shout out, just briefly, if you don't know about it, is intrinsic causal contributions, which is a very nice paper by Jansik and co-authors, which basically shows you how to specify the contribution of a specific node throughout the entire graph on the target. And this is super cool, and this helps you to visualize, specifically if you're looking at time series data, how the contribution of different variables changes over time towards your target, which can be also super informative. My final takeaway from going through that project is basically saying that if you were doing traditional machine learning data science projects, then for me, feature and model selection is often a data problem, right? So you're trying to find the best algorithm, you're trying to find the best features to explain your data, to give you the most accurate precision without obviously overfitting. But in causal machine learning, building a structural causal model is a problem that relates to the data generating process, right? So you should care much more about the underlying methods. You need to talk to the domain experts. You really need to understand the data generative process. So I think for me, this is the key distinction between the two methods and really something that we need to talk more about if we want to solve these kind of questions. Thanks.
Speaking of questions, we have some.
Oh, amazing.
I'm going to do the top two because we are running out of time. But the first one is a question. Can you elaborate a bit more how you deal with time? Do you explicitly model the time or do you simplify it somehow in your model?
So we do not explicitly model the time per se, so we don't have a time variable in there. We sort of try to attack the time component of different variables via lags or via seasonality adjustments. We do I think we tried some feature transformations as well, according to the time, some detrending. But I think we basically just embrace that time is a problem, try some different methods. And I think some of them I mentioned. But yeah, it's an issue.
Second question. Are you essentially doing transfer learning with nowcasting?
Are we doing transfer learning with nowcasting? Probably. Tough question. I'm not sure whether I would necessarily agree, but I need to think more about that. I don't have a definite answer on whether I would say we do that.
No worries. We'll do a final question then. What was the causal discovery method that you recommended?
Oh yeah, it's called FCI tiers, and it has it's a specific implementation of FCI tiers that the causaLens team has built into their platform, and it works quite well. They have a visual representation. I think you saw it. If you saw the very first talk, the intro, I think the LLM basically gave a suggestion where you saw some tiered nodes. And this is basically sort of part of the implementation of how causaLens implemented this algorithm in their platform. And it's incredibly helpful if you're trying to sort through different hypotheses on nodes.
Thank you very much, Alex.
Thank you, Alex. FCI tiers is also my favorite causal discovery algorithm, but I'm a little biased. For our next talk, we'll be staying on the topic of retail, but with a different perspective. Please welcome Dimitra Liotsu, Senior Research Data Scientist at dunnhumby. Dimitra will be exploring how to solve causal problems in practice, sharing applications, and learnings from retail. Welcome, Dimitra.
Right, thank you very much for the introduction. Very happy to be here today. So yeah, my name is Mimi Liotiu. I am a senior research data scientist at dunnhumby. Before my time at dunnhumby, I did a PhD in computer science, and it was on causal inference for measuring influence in human interactions online. And since joining dunnhumby, one of my projects has been bringing causal methods, introducing them to dunnhumby, and leading the development of the company's causal AI capability. So today I'll talk about causal AI, how we apply it in our retail problems, and share some key learnings and tips. It's actually really interesting because my talk has a lot of commonalities with the previous talk, so that's should be good complementary ideas discussed. So first of all, just a few words about dunnhumby. So dunnhumby is the global leader in customer data science. We put the customer first. We're a data science company. We're a part of Tesco. And just to give you an overview of what we do, we work all across the world with big brands and supermarkets, millions of active customers under management, and billions of baskets per year. So today, kind of the structure of what I'm going to cover, we're going to look at some key types of causal questions that we work with in retail. And then I'm going to cover some key points about answering causal questions. So the key distinction between identification and estimation, and then comparing the traditional data science pipeline with the causal one. And then I'm going to show a hands-on application to retail problems of the causal pipeline using open source tools. So I'm going to use today Pearl's graphical causal modeling approach, and this is going to be all done on observational data with wrong to interventional types of questions and backdoor adjustment, just because this is the kind of key type of retail problem that we often work with. So what are some main types of causal questions in retail? One key type of question is of this form: what is the effect or impact of some decision, some action? It might be an initiative by a retailer or a brand with respect to pricing, with respect to promotions, or with range and category. It might be a media campaign. It might be, we want to understand when the customer signs up for a service or loyalty scheme, what impact that has, or something external like inflation. So we want to understand the effect of something like that on some key outcome like revenue, sales, number of customers, customer lifetime value. There might be broader questions as well that we want to answer, like why have sales fallen year on year? What are the drivers behind, or the levers or the factors affecting something like sales? And these are some other terms that are often used in causal questions that you might have encountered. For example, even if initially we get a question and we frame it as a clustering problem or as a prediction problem, the client might then come back and say, okay, but what are the sales drivers? You build me this predictive model for sales. Great. What should I do? What are the drivers? What levers should I pull to improve my sales revenue? So then we need to switch from the predictive type of modeling to the causal type of modeling. And the key thing in getting from predictive modeling, which is about correlations, to causation is what should we adjust for? So in the kind of well-known case of Nobel Prizes having found to be correlated with chocolate consumption, the correlation went away when researchers adjusted for income. So similarly, in any kind of causal problem, we need to adjust for the right thing. So if we care about the effect of advertising a product, say an ice cream, on its sales, what should we be adjusting for here to get from correlation to causation? And there might be many relevant variables that are potentially causal that might affect these things or might be affected by these things. And the key thing that I advise is kind of thinking about reality. What are things in the world that affects how your customers think, how your stakeholders think, what informs their decision? These are things you should model. And I tend to group these things into classes of causes just for structure and for ease of thinking. So one might be things that capture traits of the product or of the retailer, like the price of the product, the quality, the category it sits in, maybe what are the category-wide sales, and then going more broadly, because things don't operate in a vacuum, what are competing products doing from in this retailer, in other retailers, what are other brands doing, what are their products doing, what are their traits. And then broadening out even more what's going on in the broader world, so what are consumer attitudes, consumption trends, preferences, things like seasonality and weather, the state of the economy, the legal landscape, like taxes on certain kinds of products. And the thing is, if we just go and adjust for everything, all of the possibly relevant causes, that can introduce bias. If we adjust for some arbitrary subset, again, that can introduce bias. So that's why we need graphical causal methods to figure out the right set that we should be adjusting for. And one key distinction when we go about trying to do this is being mindful of what methods do estimation and what methods do identification. And identification is a step we need to do before we run estimation. And that's the key sort of paradigm change when we go from traditional data science mindset to causal, because the default in data science is often we have some big data, let's mine this data for patterns and let the data speak. And we might often do this by using some advanced or cool, new, powerful method that we came across, which is great. But these methods do estimation, they're about correlations in traditional data science, AI, data science, machine learning methods can only tell us about correlation. Under the causal banner, there have been lots of exciting methods, especially developed and released recently, like DoubleML, meta-learners, and so on, lots of open source implementations. But again, these are estimation methods. They are very powerful, but you need to first draw the causal diagram and then run the identification step to then do estimation with any of these methods that you want to choose. And this is a well-known issue, not just in industry, but in academia, in academic statistics. It's been debated a lot. It's still a big topic of discussion that people really stress. So I think it's really important in a business context as well. So, there's lots of tweets and people discussing this. One is, horror story. We do matching for identification. Matching is estimation, not an identification strategy. Or, the famous Stanford prison experiment where actually it wasn't a randomly controlled trial, so that affects what kinds of causal claims you can make. People self-selected into it. Again, you might come across blogs or even academic papers where they kind of have this format where, oh yeah, we have this cool, like a bunch of covariates, cool methods, we'll try to estimate causal effects. They might or they might not acknowledge limitations, whether they can actually prove causation, but then they might still have that header, oh yeah, we found the causal effect. So be really careful, did they actually run identification or did they just use a cool estimation method? And even more recently, this blog is quite good from a few weeks ago that kind of discusses this thing where it kind of talks about how we shouldn't just start from a really nice statistical method, but because we try to answer substantive questions, we should start from our research question, what are we trying to estimate? So yeah, this is all about moving from the traditional sort of paradigm from prediction where you care about y hat and goodness of fit to your outcome, where you might not really define the problem and you might just jump straight into applying models to data. And then you might validate your models with cross-validation and so on. And then if you get asked about explainability, you might go and try calculate feature importances. Great, but this just tells you all of this is with respect to the predictive power of your model. Instead, if you want to make causal claims, where in this case you care about beta hat, so your estimated parameters being interpretable as causal effects, as well as the goodness of it. In this case, you need this highlighted bit here. You need to define and set up your problem carefully. What is your cause of interest? What's your outcome of interest? What are your units of analysis? What are other possibly relevant causal factors? Draw all of that in a causal diagram, and then you can run the identification step, which is automated in the tools we're going to see. And that gives you the set of variables you should be adjusting for. And that's what you feed into your models, and you run that on your data to estimate. And then you can validate your models in the traditional way and in a causal way as well. And in that way, you get strong causal explainability for free. So the key steps in Causal AI, if we go back to the effect of advertising and ice cream on its sales, again, we had to draw the causal DAG, sit down with our stakeholders and figure out what are some key other relevant causes, then draw all possible arrows per the semantics and the guidelines for how to draw a causal diagram. And then you run identification, which tells you in this case, yes, you should adjust for the green things, you should not adjust for the pink thing down here for this particular DAG. And then given that knowledge, you know what to adjust for, you throw that into your estimation method and you do validation. So let's apply that to an actual retail problem. Let's take a problem where, let's say we have a business, maybe a retailer, and they have a premium monthly subscription program, which is opt-in. So then why would a customer consider opting in? Because they offer some benefits like further discounts on mainline shopping and other benefits with the company's other verticals like a clothing line or a cafe and so on. So the causal question is, what is the effect of subscribing to this scheme on this customer's future mainline spend at this business? And we're going to use synthetic data throughout. So again, this is a pipeline we're following. And again, this is where the data and the modeling comes in. So the tools I'm going to look into are DoI, which is a Python library, came out in about 2018. Some of you might be familiar with it already. Another tool that's really useful is Dagity, which is an our library, and it's also implemented as an interactive web tool that's been around since 2011. This one has not really been used very much in data science. It's used in epidemiology, but it is quite useful and very intuitive to use. So let's look at Dagity for a second. So this is the URL where you can access it, and you can click and create a node, click, create another node, click between them, make an arrow from one to the other. That populates the DAG code here, or you can just start typing the DAG code straight away. And this syntax is compatible with DoY, so you can copy and paste between the two. And then as you draw your DAG, you can tell Dagity, this is my exposure, this is my outcome, so this is my cause of interest, this is my outcome of interest. And it tells you, okay, it does identification automatically for you, and it says you have two possible sets of things you could be adjusting for. So it gives you all possible minimal sufficient identification sets. And it also does validation. It gives you a list of all the conditional and unconditional independencies implied by your DAG. So with this information, you can then take this away and do estimation on your chosen set out of these. You can do that in Python, in R, wherever you want with your favorite estimation method. And when you want to do causal validation, you can test each of those independence relationships against your data. So for our problem, remember we're looking at the effect of subscribing to some scheme on future mainline spend. So this is our cause of interest, this is our outcome. And let's say we sat down with our stakeholders to pool our domain knowledge together, which I really advise. And we thought, okay, what are other relevant causes? And we thought age, disposable income, interest in verticals, and family size might be relevant. So we draw them, we draw all possible arrows between them. In reality, it's going to be much more complex, but in the interest of time for this talk. And again, Dagity tells you, okay, one possible set of things to adjust for. All these four covariates are things you need to adjust for. And as the DAG is quite fully connected, there isn't anything that's independent of anything else in terms of validation. So to do the equivalent in DoY now in Python, again, you sort out what your problem is, what your relevant causes are. This is the syntax. You can represent it again in this digraph syntax. As I said, you can copy and paste this across Dagity as well. You can visualize it. This is from a slightly older version of DoY, so this maybe looks different to the current version with nodes that are blue colored and so on, but all the results are the same. And then you can run identification. So at this step, it's important to note, you can pass it a data frame. It doesn't have to have any data in it, so you can do this at the theoretical level when you're trying to figure out how reality works. And your data frame just needs to have column names for your variables in your DAG, but it doesn't need to have any data in it. And you tell it your cause and your outcome of interest. You can plot it like this. To run identification, you run this command. So DoY supports three types of estimates: backdoor, instruments, front door. In this case, there's no valid front door, no valid instrument, but there is backdoor through this way. And it gives you the same sufficient set as we saw from Dagity. So now you know what to adjust for in your models, and now is when you can think about your data. And you need to ensure you have appropriate measurements for your cause of interest, your outcome of interest, and the covariates in your sufficient set. So that's where the point around operationalization comes in, where you need to go from variables that are underlying things in the world into measurable observations for them that are meaningful. And there are some challenges here. One thing is that there might be multiple ways to measure a variable. So if you're trying to measure health, you might measure it through body mass index, through blood pressure, or other metrics. In retail, we try to measure store performance. You might try and measure it through total sales in money, or in units, or in number of customers instead, or in terms of number of distinct categories shopped. So you need to figure out what metric is good. And yes, at your company, you might have all sorts of different metrics, and you need to figure out what makes sense for me to put in my DAG. There's also the possibility that in your company data tables, you might find composite measures. So like a column in your data that captures multiple different things, like composite scores or composite segmentations or categorization schemas for maybe your customers or your stores or whatnot. So to ensure good construct validity, so good one-to-one mapping between your metric and the variable it's trying to measure, you need to try and choose a measure that captures the underlying variable and only it as precisely as possible. So that's a really key thing when you're trying to figure out, do I have good measures? And once you've done that, and once you've collected any data you need, then you can run estimation. So you can run the previous steps on the actual data frame with the actual data containing measures that have good construct validity. You run estimation with this kind of syntax, and this is where you get your estimate and the significance. So in this instance, what we find is that when the effect of someone subscribing to this premium scheme causes them to spend 500 plus more pounds per year at this retailer, and that's it. So it's a positive effect, and it is statistically significant. DoI also offers this dot-interpret sort of method that prints this out in a more readable text. Again, that's all based on synthetic data. And for estimation, you don't need to use the built-in DoI linear regression model that we used here. Instead, you can use things from methods from stats models or from scikit-learn, nonlinear methods as well. Or you can use from within DoI, it supports methods from the EconoML package like double ML estimation. But of course, again, you need to call this onto the identified estimate after you've drawn the DAG and run identification. The notebook I can share, I'm not going to go through this now, but it also demonstrates instances of bias. So what happens if you actually go ahead and adjust for wrong variables? So it shows that confounding bias can be quite substantial. So if some of your variables in your minimal deconfounding set are unobserved and you can't adjust for them, you might end up overestimating the effect, in this case for the synthetic data, by 15% up to by 100%, so quite substantial. And then also evidence of collider bias. So if instead we cared about the effect of age on spend, in that case there would be colliders, so things we shouldn't be adjusting for. But if we had the mindset of let's adjust for everything, your estimates would have been biased by 18% up to 32.5%. In this case, it would be lower. So again, bias is substantial, so it is really important to do identification properly because it can be quite substantial. Now, finally, the validation step is where I'm just going to show the causal validation parts here. So that's where you can check your DAG versus the data. So you can go into in DAGUT, as we saw, get a list of all the independence relationships implied by your DAG, and then test them in DoI against your actual data with these methods around partial correlation. And then on top of that, DoI lets you also check your whole estimate. So including your estimate, your model that you chose to run estimation for, against the data. It offers a bunch of refuters, so that's also worth doing. So yeah, that's really it from me. If you'd like to have a look at more resources, I've got a more introductory blog, much shorter, only 7 minutes, about retail and causal AI, and I've got a more detailed talk on theory and statistical paradoxes and methods as well. Feel free to get in touch, happy to connect on LinkedIn. Some more good references, especially around what is associational, what is causal, what's identification, what's estimation, starting from estimates and not just from our data and our favorite estimation method and so on. And of course, recommended books by Pearl, and also this one, The Effect is quite good. It's fully online and it's got Python and R code examples as well. Thank you very much. Happy to take questions.
Thank you very much. We have one question. What is the underlying causal estimation strategy that DoI is using, and does it adjust to the kind of data one has?
So for DoI, you can choose, for estimation, it supports different kinds of estimation methods, and then it's up to the user to kind of just go step by step, like I showed, and run identification through that identify command and so on. So it's very tailorable to your context. You model what you think is relevant, you run the identification step, and then estimation, you can choose whatever method you want.
Amazing. We've had a final question come in. Do you go through this workflow for every question you want to answer? Probably the right thing to do, but doesn't scale well. For example, hundreds of CPGs across stores.
Yeah, that's an interesting question. So what you can do is, if you often have, and we do often have that, the similar kinds of questions that different retailers and different CPGs ask us, we can do this sort of once with all the stakeholders that you have that might give you relevant domain knowledge, and then you just have that diagram and you just share it across all cases, and you might tailor it as and if you need it, but it's not going to be as much of a time commitment because you've done all of the pre-work already.
Thank you very much.
Thank you.
Okay, thank you. For our final session before lunch, we're venturing away from retail and to a different area of causal inference. Please welcome Robert Nichols, Head of Data Science at BCA. Robert will be discussing causality in spatio-temporal graphs. Welcome.
Hello. So my name is Robert Nichols. I'm Head of Data Science at BCA. You may know us as part of the group that includes Cinch and We Buy Any Car. So we do sort of the wholesale side of that. That's transportation and sourcing of lots and lots and lots of cars. So a quick note on causality. I think one difference between science and the traditional sense in machine learning, which has been touched on in the last very good talk, is that the scientist likes to understand the phenomenon before building the model, but in machine learning we tend to just build the model and perhaps never come to understand the phenomenon. The whole field of causal AI came to my attention some years ago when I read The Recovery of Causal Polytrees from Statistical Data by George Rebane and Judea Pearl, which I'm sure many of you have read, whilst researching graph theory. And what I really loved about it is that it undermined the idea that that's two diametrically opposed worlds, or that that's kind of a binary choice. So it became clear over time that you can model something a little bit, then sort of understand it a little bit, then elaborate your model, then elaborate your understanding, of course. And that becomes a sort of conversation between the machine and the phenomenon, right? And this is really interesting, and it not only leads to better machine learning models, but it also leads to a better understanding of the phenomenon. So in machine learning, we sort of lose track, I think, of the science frequently. But even so, as a machine learning practitioner myself, it's tempting to work out if we can somehow extract the knowledge of the expert, you know, in our context, I suppose, encoded as a causal diagram, purely from the statistical data, right? Which is kind of why I love the recovery of causal polytrees from statistical data. It sort of appeals to that machine learning side of me, I suppose. So this talk is a little bit about that in some general sense, but also about spatiotemporal graphs in particular, and in particular their application to logistics networks and a few other things. So hopefully it'll be interesting and useful, but also ideally I'd like to start a conversation through it. So to give a nod to the science here, my approach is somewhat close to what's happening a lot in climate science at the moment. Some papers have come out fairly recently that use a similar approach to model weather patterns and sea temperatures, and it's sort of an intuitive way of understanding spatiotemporal graphs, as well as, of course, an important science, which is why I bring it up here. So the basic idea is that the things being observed and their dependencies on each other are a product of both a geographic proximity but also some sort of relationship over time. Delayed actions are very important. As we know from studying causality, things that happen simultaneously may simply have a common cause but not be causally linked. I'm sure you're all quite close to that understanding of that. So the hope here with this sort of framework, I guess, is that we can understand and distinguish the associational from the causal. So I'll give a little bit of a reference to these slides later, but these slides kind of give you a sense of why you might do this. I also gave some thought to this approach while studying birds with the University of Bristol. This is an urban gull. These are some pretty amazing creatures, and their migratory patterns can be very complex and can be very social. Social in the sense that they often move in the same direction at the same time. They like to move together, they make friends, they associate, and they kind of travel down the coast using cliffs as a orographic lift, which is why they're not seagulls, they're gulls. That's important to the researchers, apparently. I made that mistake many times, but you only do it once or twice. So they do trips like from the UK down to like North Africa and so on, right? And we're very interested in understanding how the migratory patterns of birds are changing as a consequence of things like climate change. It's very, very important. And so hopefully you'll see that the spatiotemporal graph allows us to model sort of the co-occurrence of things where that's relevant, for example, in migratory patterns, as well as the lagged effects where that is relevant, for example, in sea temperature changes. So by way of example here, we're going to talk about logistics networks, which is the most recent domain in which I've been applying these techniques in collaboration with the people at Google Maps. And one note is that linear optimization, a lot of people will, well, we tried linear optimization on a couple of occasions, and many people, when they talk about logistics networks, they think of route optimization solutions. The point is that in this context, those solutions don't work because you have to do a certain amount of inherently non-linear thinking, which is obviously very common to the kind of field of causality. In other words, you can't solve this with the traditional traveling salesman algorithms that you get, right? So let's get into the specific implementation. Above, we can imagine, well, we don't have to imagine, on the map, delivery locations in the UK for vehicles. And we're delivering hundreds and hundreds and hundreds of vehicles every single day, and the delivery of vehicles requires a certain amount of nonlinear thinking, because the people who deliver them, when they arrive in the location, they drop off the car, and we need other drivers who can pick up cars to go and pick up those drivers who've dropped off their cars, and you have to do this sort of associational thing. So think of the birds flying down the coast. We need drivers to do something like that. So what you have with these delivery locations is the colors represent clustering. So again, this is the extraction to some extent of our model from the statistical data inherently. We use a k-means clustering approach here to generate clusters of data. It turns out to be very effective, has some obvious limitations. For example, in urban areas, the clusters are substantially larger in terms of drive time than they are in non-urban areas. Initially, due to cost constraints, which is an important part of this project, we're clustering on Euclidean distance. But in practice, it turns out this works quite well, though you may have to subdivide the sort of London clusters and things like that, but you can imagine how it works. What you end up with is these cluster centroids. So these could, again, have problems. They might end up in the water. They might end up in inaccessible locations, et cetera, et cetera. But by and large, with a little bit of adjustment, you end up with something that can be turned into a network with some obvious issues in the northeast over there, I suppose. And here we see a network that's been constructed according to the minimum weighted spanning tree approach, which is very similar to the max weighted, well, it's the inverse, I suppose, of the max weighted spanning tree approach that was introduced to me, I suppose, by Judea Pell in the above mentioned paper. But you can imagine this is not particularly great. I wouldn't want to drive from Newcastle to Carlisle via Leeds, because that would be, well, I don't really want to go to Leeds, frankly. So what we end up doing is, you know, obviously you can get more and more complete in the construction of the graph. I hope no one from here is from Leeds. I actually don't mind, never been there. Anyway, the point is this still isn't that great because you still can't get from Newcastle to Carlisle without going via Leeds, but you can imagine as you get more and more complex with these graphs, and they become more and more complete, they become more and more sensible ways of traversing the UK with a reasonable estimate of the actual drive time from a delivery location that is represented by the point that is a centroid to or from the delivery hubs, right? So the idea is we've constructed a graph and we can send our delivery drivers along this graph, and it's much, much, much less complex than using the thousands and thousands of points to make a huge square matrix of distances. We can just traverse this graph, right? So what I'm going to do just to get on to the next side of it is I'm just going to simplify this graph and give a description of like what kind of reasoning I mean when I say nonlinear reasoning. So the blue nodes in this graph are hubs. The orange nodes are the clustered centroid points from the delivery lat longs, that is latitude and longitude points. And you can imagine if we have two drivers, one at C, one at H, and each driver needs to do two jobs. What we would want is for the driver from hub H to do job 4, then job 1, and the driver from C to do job 3, then job 2, in that particular order, in order that they end up at the same location at the same place, so that one of them can drive the other one home. That's the idea, right? And that requires a degree of inherently nonlinear thinking. that can't be solved by, I guess, out-of-the-box route optimization algorithms. So what we do in order to get to that kind of co-occurrence is we take that graph, so I've just taken the exact same graph, but I've taken out all the edges, and we kind of split it out into these time slices. So here you can imagine that sort of for a delivery network, 8 a.m., 9 a.m., 10 a.m., those are sort of sensible time periods, but that's by and large arbitrary. These can be any time periods, so for something like the climate, you might be thinking about it in terms of years and decades. If it's biological processes, we sometimes see these sort of things being used in biological processes. Got some good papers on that. They use like second-level time slices, right? But in our case, an hour over the course of a day makes sense. And you end up with this situation where you can have intra-slice or intratemporal edges and intertemporal edges. And that is to say, it's possible that if this is an hour-long slice, the distance from A to B is like 15 minutes. So if that happens at 9:10 in the morning, they'll still be in the same time slice by the time they get to B, right? Or alternatively, if it happened at 10 to 10, then the driver would be transitioning slice in order to get from A to B. Once you sort of add all the slices to the graph I showed above, it starts to get pretty messy. These are only the intertemporal slices, they're not the intratemporal slices. I didn't add those because the graphs start to get messy. But you can start to see the way it would work. You can sort of imagine the way it would work. And obviously, we're not stopping at 3 slices, we're continuing throughout the day. So it would be many, 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 many of these. So a very great advantage of this approach, and again, here we're talking about drivers, but we can think about this in terms of anything that might traverse time and space, which is quite a lot of things. And we can look at it from the perspective of the node view. So we can start thinking of the metadata that we're populating the network with. And we can start to think of drivers as a kind of spatiotemporal vector. So driver 1 is at node A at time t0, then is at node D at time t1, etc., and C at t2, and so on. And drivers 2 and 3, we can see that they are at the same time and the same place, and they need to go to the next place at the same time as well, right? So I'm sure you can imagine those are vector comparison techniques that you could use to check that a given schedule was good in the sense that it involves drivers co-occurring at a particular time in a particular place. You can also start to think of it in terms of the edge metadata. So this is what we're doing by and large in our actual scheduling of drivers over networks, is we're sort of populating the edges in the networks we've constructed with metadata that we're getting from Google Maps. And they give us like predictions, so they can give us predictions of how long it'll take to get from one point to another. And you can imagine that the edges here, we've only done the intertemporal sliced edges here. To get from A to D takes 25 minutes, to get from C to B takes 10 minutes at that particular time, at time t0. C to B is that much time, but at time t1 it might change because traffic conditions and so on, right? And what becomes really interesting about this is that subsequently we can populate the same graph, the same network with the actuals, and we can start to look at, or these can therefore become probability distributions over the actual conditions of roads and locations at given times, and you can start to imagine how you could start doing causal inference and these kinds of things on that. But also it allows us to control for risk, right? So in the hypothetical situation, for example, where D to B versus C to B were two potential competing options, well, D was supposed to take 15 minutes, but in one particular case it took 50. Even though it's predicted to take longer, it may be less risky. Things like that, right? So we can start to look at the tails of the distribution. You can imagine issue propagation being useful here. So I remember, I was looking at last year's presentations at the conference last year, and there was a really good presentation on root cause analysis in the manufacturing process. Well, I mean, it's just as critical to us that we understand how a failure in the logistics process propagates down if, obviously the drivers need to be in the same place at the same time. And it sort of resembles that root cause analysis, I suppose. It is a type of root cause analysis. So we can go from kind of knowing that a problem happened to being proactive about solving problems over the course of a day. You can also sort of see that a lot of the papers that exist at the moment in this domain are using sort of graph neural networks, right? And you can start to see how these would resemble a sort of feed-forward, a non-fully connected feed-forward neural network. So there are a lot of ways, and we haven't done this ourselves yet, but there are a lot of ways that you can start to use or imagine using deep learning to help solve the problem of sending entities down this graph, right? Which I think is very interesting. Finally, a note on graph dynamism. So you can change this graph over time. So for example, from one day to the next, the deliveries might change and the graph itself therefore might change. That's very useful because it makes your solution fundamentally dynamic in nature, which is much better than having these kind of very concrete, very immovable machine learning algorithms that are only moved by like a very intense retraining process. We found that the computational complexity of solving a logistics problem goes from, even on a very simple basis, you'd be spending hundreds of thousands of pounds trying to solve the problem at its sort of highest dimensionality. By reducing the dimensionality in this way and structuring graphs very cleverly, you can considerably reduce the computational complexity and also cost of solving the problem. And we found for even very complex and very complete versions of the network, it's still very efficient and can be done very rapidly without parallelization or optimization. So that's it really. I hope this was interesting and useful. I found that this technique is a great way of examining geospatial data and sort of telematic style data or encoding anything that you can stick a GPS tag on or might want to stick a GPS tag on. It's an extremely interesting and useful way of examining that data and modeling solutions to potentially very complex problems over that sort of space. So that's me. Thank you very much for your time.
Thank you very much. We only have one question, so if you have any burning questions, please submit them now. This question is, why not just use classic routing algorithms for driving, as it shows recent news such as traffic, etc.?
Yeah, so route optimization. So yeah, I talked a little bit about linear optimization, which is the classical solution to this problem. The way Google solves most route optimization problems for companies like DHL is through the GMPRO, which is a relatively new product. But there's a couple of fundamental problems. It's cost, computational cost. It's a very complex way to solve a problem. And secondarily, it quite literally can't perform the kind of nonlinear thing. And linear optimization algorithm literally cannot perform nonlinear processes. So it simply doesn't work.
Thank you very much. We do have lunch at 1. Just a quick note, we're finishing 10 minutes early. So if you could hold back, that'd be fantastic. But I'll pass over to Claudia.
Thank you, Robert. I will think twice next time I look at a seagull or gull, not sure. Yeah, so in a few minutes there will be lunch. We ask that you kind of hang here to give everyone a chance to set up and to not disrupt the other stream. While you're at lunch, feel free to stop by our demo room. You'll get to see the platform, ask questions, and meet the causaLens data science team. And then we'll come back here at 2 p.m. Don't forget, if you come back, it's full. There is the breakout room across the hall. Thank you. Where's the demo room? The demo room is downstairs. Hi, welcome back. We'll start our next session. Again, a reminder to ask your questions through Slido with the event ID on the slide. So today we're kicking off the afternoon with an exciting panel discussion called Exploring Causal AI's Potential in Responsible AI and Risk Management. I'm thrilled to welcome our panelists, Maria Accente, Head of Public Policy and Ethics at PwC, and Ari Cohen, Chief Data Officer EMEA at Macquarie Group. And we also have our moderator, Oliver Matthews from causaLens.
Cool. Hello, everyone, and welcome to the panel on AI's potential in responsible AI and risk management. I'll hand over to our panelists to do some brief intros, and then we'll jump into some questions. So maybe Ari, starting off with you.
Sure. My role is Chief Data Officer for Europe, Middle East, and Africa at Macquarie Group. If you haven't heard of Macquarie Group, it's the largest infrastructure financial manager in the world, headquartered in Sydney, which means lots of 11-hour time difference and lots of calls at odd hours of the day. Started my career in data science and then moved into doing more data management, and these days data and AI management is a big topic and big theme.
And Marie?
Maria Accente, I work for PwC UK, professional services firm, and my role is to look after AI public policy and ethics, but previously I've been looking after responsible AI. In fact, we are the first ever company to launch a product and a philosophy of responsible AI, and puts us in a good position that we've been looking into what responsible AI is and what it means for a bit.
Amazing. Well, thank you very much both for joining us. So Ari, maybe starting with you. The financial sector is somewhere where transparency and regulation are obviously key themes. What do you see as the most pressing challenges when you're trying to apply AI within the sector? And maybe as a follow-on, what do you see as Causal AI's potential role in financial services?
So I think a key theme, what we've seen, I'd say, in the last decade, is as AI's capability has started to increase, and we've seen you're able to do more things with it. Regulators and other people have noticed this. Companies have noticed it and are looking to deploy it in new ways. And in financial services, and actually it's something that's playing out cross-sectorally, so we're seeing it across all sectors. There's concerns about controls and how do you manage and govern AI responsibly. So as of last month, we saw the EU AI Act come into force, and a bit like GDPR, a lot of people expect that will sort of set a watermark for AI management, and we'll see similar things, or AI governance, we'll see similar things come out from regulators in other countries. But we're in a phase now in financial services where the financial industry regulators are talking about what their specific approach is going to be to AI. So EU AI Act is across sectoral legislation, applies to all sectors. If you're in banking or any industry, if you're in health, your regulators are going to be having discussions about how they should be regulating AI in your domain. But all, of course, the question is, how are you managing AI? How are you ensuring its responsible use for your customers? And these are very thematic topics in financial services and where I am at the moment.
Amazing. And do you see Causal AI playing a role within that, or have you applied that in Macquarie Group so far?
Yeah, so Causal, what I like about Causal AI is, so it's essentially generative AI in the type of transformer architecture that's at the heart of it. Everyone knows it hallucinates. Mathematically, it cannot be precise. So it's about how do you ground that and put controls around it. And I think what fascinates me about Causal AI, and we saw it with the recent release of O1, is that logic and reasoning is sort of a grounding point for artificial intelligence. And chain of thought is not as formal as Causal AI mathematics or reasoning, but we are seeing this trend towards, okay, we can throw a deep neural network at something. But for me, the trend of making it explainable, grounding it in something, whether it's through chain of thought or Causal AI, which is more formal, is something that can be an anchor and make the technology more transparent, more understandable. And I think that's the opportunity.
Okay, amazing. And building on the Gen AI theme, Maria, responsible AI has always been a concern for companies, but with the advent of Gen AI, we've seen it kind of go straight back to the top of the priority list. And so I assume this is something you're seeing a lot with your clients at PwC.
Absolutely. So for a while, since we started in 2016, 2017 to explore what are the implications of AI, why AI is special compared with previous evolution of technology. And we discovered pretty much that AI is going to be extremely disruptive, transformational. It's pretty much putting a Ferrari engine on a Trabant chassis. It's going to blow up the chassis if you don't have all the parts necessary to cater for that engine. And we understood there is a role to think of how do we manage a technology that unique, that operates 24/7 at that scale, has a certain degree of autonomy and adaptability. And it was only in 2023, which is last year, companies started to prioritize and understand the negative implication of AI because they haven't seen it, right? But now they were able to be part of the supply chain of AI, playing with ChatGPT. They started seeing firsthand how he hallucinates, being able to experiment or try to jailbreak some of the safeguards, and suddenly became clear, especially for C-suite, that there isn't an option to have responsible AI practices on top of it. The engineering practices is mandatory. And that was like the aha moment for many of them, but the community has been gathering evidence and trying to make the case for the negative implication for quite a while. And then since we are here and we have this visibility, the question is how to do it, because there is always a risk of overdoing it and applying too many rules and safeguards that will obviously throw the innovation off guards. So how do you build that program that in a way mirrors your ambition with AI? We can't really talk about responsible AI if you don't do much on AI, and we've seen this with a lot of our clients, but also in the same time being able to recognize that this technology, Ari and I were discussing earlier about agentic AI and how no one really knows how fast will be coming and how disruptive will be. Disruption will be coming, you like it or not. So you need to have this agility to respond to those risks. Financial services probably is one of the best prepared industry because they're highly regulated. They have a robust risk management approach. But if you go in outside financial services, you go in private sector, you go in retail, you kind of have a weaker and weaker risk management mentality. So you need to first of all educate, again, this is not optional, this is not a nice to have, it's a must to have, and then deploy it in such a way that is balanced and proportionate and agile. And I think that is the hardest bit. But again, Gen AI has at least gave us a peek into how disruptive it can be, but also how to stop that speed of disruption by putting the human back in control. And I'm hoping that that's going to be the approach going forward always, is not allow the AI to go too far ahead before us coming and checking if that's right with our values, with our objectives, and so have you.
Okay, so it's about balancing how do you push innovation forward without going too far ahead and sort of bringing in risk or unnecessary risk into the process.
Absolutely.
Okay, cool. And I guess amongst your clients, have you seen an interest in causal approaches, or are they taking kind of a different view into this?
To be candidly honest, no.
Okay.
Mostly because what I see is responsible AI programs rather than the full extent of the type of AI that's being built. However, when I researched for our panel and I was thinking, why could causal AI be such a massive difference to what we do in responsible AI, is because one of the key issues that responsible AI programs try to solve is like, what are the implications of the AI system? Not just right now. We know that there are some implications right now in terms of potential to discriminate, potential to create or further exacerbate inequality. But what will happen on long term and even medium term as we see those systems increasing their autonomy and adaptability? And I think from that perspective, I can see causal AI being part of the solution rather than being the problem. So what we're trying to do with responsible AI is actually, is the solution to the problem the AI is displaying, is exhibiting this implication, those type of impacts. Causal AI can help us identify what's the root cause of discrimination and bias. And we kind of have a bit of a understanding, but it's quite fuzzy and it's not as precise it should be to say, in terms of discrimination, that's the reason we ended up discriminating in some cases. And we've seen so many AI systems that have been developed with the best engineering, with the best known to date responsible AI practices, being chatbots, being AI hiring assistants, that turn out to be discriminatory. And the question was, but why? What have we done wrong?
Cool, yeah, no, makes a lot of sense. Ari, in your role as a Chief Data Officer, how do you balance this kind of trying to push innovation far forward and roll out new things into the organization with a natural risk that comes with these new technologies?
Yeah, it's a great question. I think all companies by their nature are going to be seeking the reward that AI has to offer. How can increase revenues, increase efficiencies, increase automation, and at the same time, many companies, particularly companies in sectors like financial services, insurance, healthcare, where the risks are higher, have more developed risk frameworks. So in my role, working at the bank, we've got established 3 lines of defense practices. So whereas on the one side I wear a hat and encourage enablement of the technology, how can we get all the benefits out of it? I'll also make sure I put on my risk management hat and think, okay, what are the preventative controls that we should be talking about? What are the detective controls that we should be talking about? And I think it's still very early days in terms of AI risk management and the type of practices and processes that companies are going to develop around it. Again, if you go back to privacy as an example, when data privacy first became a thing, you know, everyone was like, oh, is this a thing we need to do now? Didn't realize we needed to do that. And you look at it today, all of the controls are in place, all of the processes are in place. We're still seeing some companies fall short, and it's still a challenge. I'm not saying it's gone away, but I think with AI, we will similarly see a control framework that gets built around AI. We'll still be able to go after all the rewards and huge potential AI technology can offer us as a society and in banking. But I think we'll also see that risk management framework continue to develop, and you know, it of course needs to.
Okay, maybe moving on a little bit to how we manage this within the organization. And so, Maria, often the technical side of AI and the ethical side of AI are kind of addressed by different sets of stakeholders. And so what role can kind of the technical experts play in ensuring that AI is rolled out responsibly? And what role can the more kind of ethics-focused stakeholders play to make sure that innovation is not stifled?
A huge one. And many engineers might not like my answer fully, but ultimately, when it comes to AI, we need to be thinking of having a clear accountability framework, right? Who is in charge of which part of the AI ecosystem? Because we've evolved our understanding of AI from purely a technology or engineering product into a fully socio-technical ecosystem. And that was quite a bit of a journey we've taken in the last 6-7 years to move from defining AI as an engineering asset to defining it as a socio-technical system, which is so important. And in that one, we need to be able to define who's responsible for what, especially when, again, agentic AI is coming. That was going to throw everything in the air, from liability to managing risk. It's even more important for us to have a clear view. However, when I'm always advocating, it has to be a proportional accountability. You can't always go back and blame the engineers when a system or an AI system goes wrong. It might not be similarly with what happens, when a plane crashes or a car crashes. and you will say it's an engineering fault. You need to be able to look at the whole ecosystem because AI is so intrinsically linked to its context is operate. So first, having this clarity about an accountability structure. Secondly, it's about transparency, but it's not just about having the right information. It's how do you communicate? How do you build the dialogue? For a long time, has been this disconnect between the technical world and the business world. I have a business degree, I've been running businesses, and I came from technology with this business background. And I've seen myself as a bridge, having had to learn the technical language. I still struggle, still kind of a complex Klingonian language, but translate it back to business because that's where the decisions are being made. The technical experts, and I've seen some of them doing brilliantly the journey back the other direction than myself, doing the same, is being able to demystify and dissect those very complex engineering details so that those in decision position are able not only to take informed decision, but being able to have a bit of a dialogue. Because business understands technology, engineering doesn't, and vice versa. So secondly is about communication. And thirdly is about incentives, right? So why would I do the right thing? And I think that is a more of philosophical question and leads back to what are the values of our companies. When you have an established company like ours, 170 years old, you have very robust corporate governance and ethics structure. But as you go towards the small, medium enterprises, very much the values are the ones fostered by the founders. And you have to have a very strong moral compass that will end up defining the company culture where good decisions are being made. We won't be able to really develop AI that's truly ethical if we rely solely on regulation, on hard rules. We need to be relying on good people doing the good thing.
Okay, yeah, makes a lot of sense. And so the way we think about this at causaLens in terms of, to your point around bridging the tech and the business stakeholders, we have nice frameworks for sort of infusing domain expertise into models alongside the kind of data-driven approach. And so maybe a question to both of you just to finish off, and then we'll ask some from the audience, but how do you think about it being a case of technology choices when it comes to bringing in responsible AI, and how much is it more about frameworks and governance and kind of things aside from the technology that you've chosen?
So my answer there would be, my thinking would start with the people. So I suppose like any good technology design starts with people. Start with frameworks that are around people. What are our accountabilities? What technology will be built around us to do things we want it to do? Once you've established a framework with your people, then you go and you seek out technology that's going to enable it effectively and as efficiently as possible. Technology, in my experience, can help when it comes in locally and solves a problem fast. But when you want to do it at the enterprise scale, you need to decouple it from the tech first and then go seek the tech second.
Look, when you travel to a new country, a destination, you need a map. So you're not going to go without having a bit of a structured approach of how you get there. Yep. It's the same with the frameworks. We kind of need it right now because we are in uncharted waters. So we need that. But in the same time, we need to be thinking two layers. One is the product layer. It's like where you're going to build a product and you're going to apply it for specific problems that need a solution. But the second layer that's probably a bit ignored, especially in the tech sector, is the disruption it brings to the world we know it, which is how do we need to adapt what we do, our organizations, our ways of life, in a way that will cater not just for the AI as a solution, but AI as a disruptor. And I think we're nowhere near to be ready for that. We are very good of applying those frameworks at the product level and say, this is a problem I'm solving, this is a solution, AI being part of it, and that's what I need to do to ensure that everything works accordingly. But when we look at the ripple effect it's going to have on how we operate, we don't know what to do about it. But we're doing a better job, definitely. And having been part of the responsible AI conversation for those years, I've seen how fast the conversation not only has evolved, how much we've learned to collaborate with each other, and how better prepared we are even than we'd been 2 years ago.
Okay, amazing. Thank you very much, both. I'll now hand it over to the audience for some questions. So I think over to you, George.
Yeah, amazing. Thank you very much. We've got a couple of questions coming in. I think you've definitely touched on some answers here, but maybe some clarifications could help. So first question is, risk management at organizations is often seen as a blocker to new tech adoption. Is there a way to frame risk management as an enabler for new tech like AI?
It's a very good question and a very valid one, I would say. And the answer, my answer will be, when you think about building a car, I like driving, would you put that car on a road without testing it, without putting airbags and seatbelts and making sure that the brakes are working? No, you wouldn't. You wouldn't put a plane in the sky and fill it with passenger if you wouldn't go through a lot of safety. That's the role of AI risk management, is to make sure that the digital products, even if they are in the virtual digital world, will not end up harming individuals, groups, and the planet. So as we have done, we have gone through this process of making the cars and the planes and the food safer, everything safe around us, we have to do it for AI. So it's not negotiable. And in fact, a good and robust risk management approaches will allow us to be much more innovative and accelerate not only the innovation but also the trust we put in this technology.
I would agree with that. The brakes are there to make the car go faster. When you zoom out, you can see that picture, and it's sometimes, depending on your industry, you might remind someone, we can't operate without a banking license. We need to make sure that we can manage the risk. When people, yeah, I would say typically, if you're trying to get that message across of risk management as an enabler, help your stakeholders zoom out a little bit, because they're probably just feeling like, this thing's going to take me another 3 months.
Amazing. Final question here. Social norms vary across the world and ethics evolve in time and differently in different cultures. To what extent can responsible AI be consistent globally?
Wow, what a good question. Thank you. Thank you for asking it. Where do we start? I think it's the realization how many different value systems exist around the world and how we ended up, to a certain extent, not really accounting for them in the early stages of responsible AI. However, in 2021, UNESCO has worked with hundreds of, not thousands of experts from around the world, representative of 189 countries, because I think US was out of UNESCO at the time, to draft the global universal ethical AI principles. And it's a very good start. However, those principles still reflect a very Western approach to ethics. There's much more research and also worked in other parts of the world, specifically in Africa, to determine what is their value system. Obviously, they haven't had to think about it, bless them, with the history they had. But that was the perfect moment for them to come together and to actually rethink is what are our values and how do we want those values to be reflected in AI we build, but also the AI that's being imported from the Western country. But I would say the best start we have right now is this UNESCO AI ethics principles that have been now used to inform national strategies. We also had the OECD principles that, again, have been informing the work of the regulators. So there is this harmonization that happens, is a bit slower. However, I will still encourage countries and regions, before embracing those, to start asking the question, what are the values we stand for, and how do we want AI to reflect our values or not?
And I might just add to that, I think there'll be differences with how various countries' value systems look at AI. But I think a core one will be AI is here to serve people, and as use cases bear more risk, I think we agree we need safe deployment. So it's fine if I'm using AI in e-commerce, but once I've got AI embedded in a nuclear power facility, well, that's a very high risk deployment. So I think we need to make sure our AI is safe. And there'll be differences, but I think there'll be some common ground across the world.
Amazing. Thank you very much, everyone.
Thank you.
Thank you very much to our panelists, and we had some very interesting questions. Our next speaker is Michael Williams, Principal AI Research Scientist at SLB. Michael will be discussing semantic causality and causal AI, enabling discourse for trust and real-time root cause analysis. Welcome, Michael.
Okay, thank you. So yeah, I'm Mike Williams, and I work for SLB. For people who don't know, SLB is the world's largest supplier of energy services, and energy services is at the end of where energy is created and people own it. For example, an oil company like BP might own an oil field, and their SLB would drill wells, make measurements, and assist essentially in the engineering tasks. The symbol of the SLB is up there in the top corner. The picture shows what the world needs to do for the energy transition. So net zero is in the middle, and the blue curve is the carbon that we will emit, which is far more than needed for 1.5C, and then the carbon that would have to be stored for the rest of the century to meet the original Paris Agreement. So essentially, we look at the world trying to deliver the affordable, secure, sustainable energy. And in terms of causal AI, I'm going to talk about a very practical, how we've practically deployed it. This is how we deploy it today. This is one of those cases that's quite close to the example they gave at the end of when you put AI in a nuclear power station, you better be sure it's safe. The case will be relevant for other industries where you have things that you plan for that you want never to happen. When they happen, you analyze them to make sure that they don't happen again. So they're the most data poor case. In our case, I'm going to talk about what we call stuck pipe. So this is, you want to drill a well, it's 5 kilometers long, 10 kilometers long, it'll have about this diameter. To give you an idea of the engineering challenge of drilling, if you scaled this down to a human hair, so this size scales down to the human hair would be 2 to 3 meters long. The needle would be on the floor over there somewhere, and I'm trying to thread it by spinning the other end between my fingers and thumbs. And that's kind of what a directional driller is doing. And if it gets stuck, you've spent time and days and potentially millions of dollars getting to that point. And now all you have is a hole with a lot of steel in it. So it's incredibly expensive, time-consuming, has all those features of the situation where you would do everything you can to not do it again. So how do we start to look at it? The first thing we do is on the semantic side. So I'll talk first semantic causality, and then the causaLens, causal AI numeric side. We build the smallest, most generic picture we can of the system. So this, you see here, Peter Gregory, he's a big proponent of this approach. This is super generic. So people have talked about time and how do you manage time in different cases. And in general, in the most abstract version, we don't see time. Here, I've got states of the world, activities that get done, and then risk is essentially identified as undesired events. This gets paired with other things that we know. So if you look at the loop around the outside, that's really a state machine. If I've got a world state, it presents some preconditions that could allow activities to happen. Those activities have effects, and they change the world state. And then separately on the right-hand side, you'll see a little box in a rectangle called SOSA. This is sensors and actuators. The nice thing about engineering is there's loads of companies all doing it. So in some areas, like with observations and sensors and actuators, the industries, and this is particularly the automotive industry, have got together and made some definitions. And where definitions exist globally, we'll use the piece that we need. So how do we get this picture, which is essentially going to be able to build any risk model? In terms of timeline, if I'm looking at the climate problem, my activity is I'm burning fossil fuels. The undesired event is I'm going to melt all the ice caps, and that will present as a world of storms and dramatic weather that we don't want. Separately, at the actual drill bit, I might have a little piece of AI that's deciding whether to drill faster or slower. And then the timelines are on the seconds and milliseconds. So essentially the context matters, and we want to be able to instantiate our app for the context that it's given. The way you can apply causality in semantics is almost as simple as it looks. You write out these direction of causality that you're going to enforce. You say, these are the only things that you can say. So it's almost now like a language. If I want to do something, I have to define it as one of the 3 classes of nouns. I can only do the kind of 7 different verbs. This gives us an approach called guided authoring. So here's an example, which comes from geology, which I try not to go into too much. But basically, every rock is different. One of the rocks you typically have to drill through to get to a geothermal pay zone, which is a steam-filled crack in a volcanic region, is a layer where there's clay. And anyone who's got clay in their garden will know that when it gets in contact with water, you get a lot of rain, it gets really boggy. So the issue with drilling through clay, which is the paragraph at the bottom here, is that we're using water to lubricate the drilling process. I mean, water with a set of chemicals in it to give it the properties we need. This is going to come past the clay all the time. The clay is going to swell, and over time it's just going to grab hold of the drill pipe, and then it will get stuck. And as I said, before it gets stuck, that's super expensive. So this is one description of how I could get stuck. The nice thing about this is that the next step, we've done the first 2. People can think later, packing off, is that the undesired event? Or was that a state of the world? Stuck pipe? But essentially, you can map from human text into what's called a machine-readable form. This is one area where LLMs are pretty useful because you can ask them to take this engineering manual, map it in, and then you can check it because you can say, have you given me cause effect all the way down? You can ask, can I turn this chain into something that a geologist would read? And when the geologist reads it, they can verify it. So this is one way that we use LLMs within the process of building these. But what you end up with is a long line of cause-effect chains that are all essentially declared independently. At the top here, I've called these questions. Again, another good way that we can get data for the final training part is if we set each of these chains with a question at the top. LLMs are pretty good at saying, here's a PDF, here's 10 questions, give me the answers as yes, no, lower, medium, higher, those kind of things. So again, for data capture, it's quite good. The last step in the kind of semantic side of the causality is to build the initial graph. Now, the initial graph has common concepts. So wherever there's a common concept, you just overlay them one on the other. Separately, and particularly in engineering cases like in energy services, you might have chemistry, you might have fluid flow, you might have finite element models of big engineering structures. In those situations, we can run physics simulation models to build a conditional probability table for that particular node. Other nodes will be latent nodes where we don't have any information. And then some nodes are those question nodes at the top. So once we've got an initial graph, we can lay it out. Here is the left to right, but it's essentially the same as the top to bottom that you've seen, where things to the left can cause things progressively to the right. This is where we're now starting to bring in the numerical side. So we've populated the nodes that we can populate from simulations. We've got nodes that we can have questions. Maybe this covers most of the green nodes. Then we do the training step, where we've got those questions and answers, historical data, where we would, call the fit function. But what we find that in addition to causal discovery, where we might be trying to look at how many paths are relevant, we're also trying to look for redundant concepts. Because one of the issues with semantic, and to give you an example, if little bits of rock sink back down to where my drill bit is, they could get stuck. So I could get stuck pipe from sinking cuttings. The normal operation I'm planning for is to flow fluid all the time, lubricating everything, moving the cuttings away. So when I get all the information, I'll have a concept, which we call cuttings transport, of how the design moves the cuttings away. And I'll have another concept from all the times things went wrong, where somebody said, well, the cutting sank, and then the drill bit got stuck. So I need to use analysis of the built graph to find that there are redundant paths, which are essentially carrying identical information. They're either 100% correlated or 100% anti-correlated. And I come back to the expert and I say, you've got these two things, cuttings transport and sinking, and I think they're the same. And that's one element that we have to bring. And on top of that, we use the other kind of causal discovery tools that you have in causaLens. This is somewhat of an open question right now. So when I said we fit to the historical data, the reality is when you analyze a risk situation, you rarely agree that it was the same issue. And there are many, many reasons why you might consider your risk is high, mostly related to why the mechanism by which you might fail. Now, in our case, we've been able to narrow it down to 3, but this means that when we fit, rather than a straightforward optimization, as in, these are the questions, and the answer is the chances of solids causing pack-off, which is the little bits of stone getting caught around the drill bit, is not the only thing to tune to. And each of these will be different depending on the geometry, where you are in the world, and the kind of well you want to drill. So ideally, we want to bring multi-objective optimization methods to the tuning of our causal AI, because the context in which the person's making the decision determines that sort of fine-tuning element. And if people are working on this, I'd be interested to talk to them, because it's an area where we're at the beginning. The area where we most use kind of the tools similar to causaLens tools is in learning subparts of this graph. So there are various sections of this graph where we can get information from what we call on memory. So it's recorded all the time at the drill bit down hole, but we can't get it to surface. That's because the only communication, there's no radio communication, there's no fiber communication. So the communication is a method called mud pulse, which is literally pulses on the mud. So you can do kind of bits per second. Typical uplink is about 7 or 8 minutes of time. So you don't send information you don't need to send, and you certainly don't send it all the time. It's a little bit like when NASA first went to Mars in the 1970s, the kind of data rates they were playing with and time issues. Oh, thank you very much. But then after the job, we can have high-frequency accelerometer information about all the vibrations. And from that, we can learn, and then that learning, which we can do with the counterfactuals, gets fed back both into the operation side, but also into the decision-making side. So to give you an idea how the fine-tuning works, here I've got green, amber, red, corresponding to extraction of the answers to questions from historical cases where things were fine, things were kind of fine, but we knew what to do, and things where we maybe had non-productive time. And the way we use this right now is we do the calculation on the network. After we've got the calculation, we've got 3 different levels of risk. And what we do is we then use that in the search of the training set, because in real time, this graph you see here, which goes from the low risk to the high risk, gives you a broad picture of where you are, but it's only relevant across the kind of 3 axes. So here, their issue was the center one, which went from low to high, and the other 2 were much more situational. Every well that's drilled in this area has these risks, and we manage them. And so it's about finding what's relevant. Some of this arose out of a comment that one of our clients, early adopters, made, that if they had nothing at all, the only thing they'd want was to be given the report from the people who drilled the last well and a list of what they did and whether what I'm doing is different, just because historically that's what you would have had. And the goal is to always do better than the decisions people are making today. But that actually led us to a method that's turned out to be very powerful. And in a couple of slides' time, I'll show you how the explanation side of this system work. First, I'll do a recap. So to put together the numerical causal AI approach with the semantic approach, define the smallest piece of your semantic picture that you need. Then your SMEs can attach essentially to the nouns. They're restricted to only say particular types of statement, and you check that those statements are causal. This will overpopulate a causal knowledge graph in that some things will be antonyms, synonyms that you need to discover and help them weed out. And then you want to deploy it in real time. So in real time, this is all about how much time do I have to actually answer the risk question. So this is a behavior tree. Typically, we use behavior trees. They're used a lot in robotics. We use them for the automation of the gross tasks. So usually the AI in a behavior tree system is giving you a list of tasks, and they've all got recovery mechanisms and things like that to keep a machine going. So in our case, there's a trigger. Why do I need the risk? Sometimes this is an alarm that comes from a machine learning time series analysis trigger system. Sometimes it's operational, and it can be a formal operational decision. This then chooses the risk I'm interested in. And as I say, normally, if I'm interested in a risk that's stuck pipe, I'm actually interested in 2, 3 different categories of risk, which all combine to lead to the thing. The next step is the planner. So a planner is a goal-oriented task generator. So I've got many things that I can calculate. Even though it's hard to get data from downhole, I've got lots of data at the surface. I'm pumping fluids around. I'm moving the drill pipe up and down. I'm pushing on it. So I've got to choose, in the amount of time I have to make the decision, how to get the most information out of all of those little pieces of AI that I've trained and any kind of causal AI extra nuggets that I've got. And so what the planner does is it says, well, this is the compute you've got. These are all the sensors you brought. These are all the kind of decisions. It's fed the causal network, so it knows which questions could be answered, and it does like an information-led, if I have the answer to this, which question should I ask next? Builds a structure. It executes that plan. This is a decision in the real world, so the reality is not everything's automated. Some things, it turns out, are surprisingly hard to automate, surprisingly straightforward for a human engineer to just go and have a look or take an opinion on. So typically, it will pre-populate a questionnaire with some gaps. And if the engineer can fill in the gaps, or if the engineer can recognize some of the questions have been misanswered, and then they'll go ahead and do that. So this is, again, as they were saying, actually, usefully in the ethics discussion, putting a human there just before the decision-making part. So then we do the causal network calculation, and it returns the report. And as I say, the report is made half of a report on the current case and the current risk, and then half the set of examples from the training data processed similarly, so people can do a comparison for themselves of exactly where they are. This is a different view of the same thing. If you're people who did computer science or software engineering background will know sequence diagrams. So time basically goes down. Here I've got a team lead, a geologist, and a well engineer. They're representing a whole team of people. And on the right-hand side, I've got the trigger, I've got those autofills, and then the stuck pipe advisor is the causal AI system. And essentially some things, like the geology I'm going to drill through, can be quite well known before time, in advance. So I can be given, if you like, a set of answers to parts of the questionnaire, depending on what you expected to drill in the day. Then at some point, and in this case, this came from the geothermal case, so they drill through, they find steam. As soon as you find steam, the water you're using to lubricate the drill string will flash cool the steam, so it will literally get sucked away. Suddenly you're drilling blind, the cuttings can't be moved to surface because all the water's going away. You need to assess the risk. They get the request for their autofill, the planner gives the execution. Then it goes back to the well engineer, they fill out what they know, then comes in the digital report and the team have an exchange to figure out the mitigation section. So we can't tell them the risk of getting stuck is 70%. They find that no use at all. But what we can do, and this came from Maruna Clinchu at the Heriot-Watt University, so we can give them a flow chart that isolates why their risk happens. In this case, they changed, this is the bottom hole assembly, so this means they pulled all the way out the hole, they put different bit on, they went all the way back in. And when they did that, they had observations. Firstly, was it tight, difficult to get out of the hole? The caliper is the size of the hole, and that identified that the thing they need to look at right now is the geometry. Now, if I tell somebody, actually, you've changed the size of the bit and your hole's quite sticky to get in and out of, that's more valuable than 70%. So, finally, this is how we build a system. So, I'm happy to answer questions on how the system can be built or how you could build one. But we do have questions. What is the extent to which this approach of teaming the answer with search, how far is that going to get us towards the kind of validation that you really want to verify the safety? Is that okay?
That's perfect. Thank you very much, Michael.
Thanks, everyone.
We have one question, if that's okay. The question is, do you work with AI ML models on the edge or on gateways or in the cloud? Also, do you use Causal AI in acoustic emissions?
So, yes. So we use we have the system, it's edge. So this is deployed at edge for the well site, but we have what we call well site, town, and cloud as the three categories. Town, we have the real-time center, so that's both, it's not just AI, but it's also physical engineers who have more time and effort to kind of review the process. And then cloud is for big compute, but it's a longer cycle. So essentially we work backwards and forwards. When a decision has to be made at the well site, that's why we have the planner figure out what we can do with the compute and everything like that. That piece is for that edge section, yeah.
Amazing. We have one final question. We can squeeze it in. Did you also apply and combine formal model checking methods?
So formal model checking methods is another talk I'll give on a different day. But yeah, when you want to move AI that you've trained, essentially black box in the cloud, to the edge or to a small device, the general experience is that you won't carry, the training won't carry, because anywhere where the AI has picked close to rounding error values for any weights, then they're ultimately not really copyable. And so there are big, big issues getting the AI that you've trained deployed on small devices. I love that topic, and I won't say any more now because it's for another day.
Michael, thank you very much.
Thanks,
Thank you, Michael. For our last talk, we'll return to the banking sector, but with a focus on a specific use case. I'm pleased to welcome Clara Higuera Cabañas, lead data scientist, and Javier Moral Hernandez, senior data scientist, both from BBVA. Please welcome them, and yeah, thank you.
Hello, thank you so much for having us. We are very happy to be here. I'm Clara Higuera, and my colleague who will be presenting with me, Javier Moral. We are data scientists at BBVA, AI Factory. BBVA is the second largest bank in Spain, and we have a lot of presence in South America and also in Turkey. And the AI factory where we work, it's an area where data scientists, engineers, and product experts work together to solve business needs through building data products. From business needs or business problems like recommender of products or fraud detection, or the area or the field that we're going to cover today, which is debt collections. So I'm going to give a bit of an overview of what we're going to talk today, which is actually our own journey from approaching a problem from a predictive machine learning perspective to move to a causal ML approach, and why and how we did it. So we're going to explain the problem. We're going to explain how we approached it from the predictive ML approach, then how we approached it from the causal ML approach, and what the advantages and the limitations that we surpass from the previous approach, and then our own lessons learned, so maybe they can be helpful for you in your use cases. So the problem that we solve is a quite classical problem in debt collections. So we do analytics on people that have already contracted some debt with the bank, like loans, mortgages, or credit cards. And unfortunately, sometimes customers face difficulties and they start not being able to pay or miss payments, and they go into default. So usually financial advisors, what they do is they do analysis on how to come up with solutions to minimize loss and also help clients. And there are a variety of solutions, financial solutions. And one of them is when the bank is willing to take on part of the debt of the customer if the customer commits to repaying the remaining debt in a single payment. So in this process can have an outcome of like success or not success. So success would be when the customer can repay the rest of the loan. So this is the general way of working. When the problem came to us, so we were asked to build a model that recommends the percentage of partial loss that can be offered to the client. And also, as in the previous talk, the financial advisor would be always the final decision maker. I have to say that this use case is still in a research phase, but we have done all the end-to-end and come up with very insightful results. So our goals are, first, can we find the optimal percentage per client according to probability of repayment success? And second, can we understand the effect of this percentage of assuming partial loss by the bank on repayment success by the customers? What is the data that we have? We have only historical data of these solutions offered by financial advisors to customers. So the journey is the client is having difficulties, then the financial advisor analyzes the situation, offers the solution, and then we can see whether there was a payment success. So one important thing is that we only have observational data. We could not make experiments, so they don't come from a randomized control trial. We have very, very few observations, 8,000 samples only, and our data is high dimensional. We have a lot of variables, up to 400 features that we have to decide which ones are the most important. The outcome is binary, like the customer was able to pay or not, and the treatment is continuous. So from now on, I'm going to describe the treatment as a percentage of discount within a specific range, and it's continuous. And there is no non-random allocation. So the majority of similar customers assigned similar treatment. So we think that we are facing a kind of cognitive bias by financial advisors for this fact. So on the plot, you can see the empirical data, so the buckets of percentage of discounts on the x-axis, and on the y-axis the observed success rate. And one thing that we can see is that we can observe there is not much difference between like low percentage and high percentage. And we'll talk about that a bit more later. So we started this problem from a predictive ML approach and see where we got where it got us. So in-depth collections, we have a ML pipeline that we have optimized to usually for classification problems that we reuse. And in this case, so the first step is feature selection. We have a lot of variables, so we want to find the most relevant ones that have the most predictive power. And for this, we do an iterative process using methods like recursive feature elimination or permutation feature importance to reduce that set. So once we have these variables, we fit an ML model to learn the outcome using these selected features and also the treatment or the percentage. Afterwards, in order to calculate we calculate the outcomes for all customers for different treatments, or we do several different inferences with the model for all clients and different levels of treatment. And with this, we calculate the curves in the validation set. So because we have a continuous treatment, we can calculate those curves, that those values can then be included in a cost function to optimize that percentage. So the results that we found we got was first that treatment was not one of the variables that our selection method found as most important, but we still included it. We trained three different methods: logistic regression, XGBoost, and a neural network. And here on the left, you can see the percentage of discount and the probability of success, and we can see similar results as the empirical data. And also, if we calculate the marginal effect curve, that makes the difference between one percentage, for example, 30% and 25%, the probability of success is it's almost zero. So this is counterintuitive. It's and also business experts say it's not possible, that this doesn't have any effect. So we are probably here having a problem or a confounding bias problem that is distorting the treatment, the effect of the treatment on the outcome. And so we move to a causal ML approach for 4 reasons. One, we don't have experimental data. We couldn't make experiments because it would be unfair to offer different percentages to similar customers. We need to address this potential confounding bias in our data. We want to estimate and understand the effect of treatment on payment success, and we ultimately also want to generate unbiased counterfactuals with different treatment percentage, so we can get to that personalized percentage. And so we want to make decisions, and we're not so much interested in very accurate predictions. And Javi is gonna tell you now about the causal ML pipeline that we have created for this problem.
Okay, thank you, Clara. So what steps do we follow when facing this problem under causal ML? We've developed a pipeline that goes through the essential building blocks of causal inference, but also addresses the technical challenges of our data. So we start with our observational data and the domain knowledge provided by our financial advisors. And the first thing we do is dimensionality reduction. We focus on selecting the most important features and removing the noisy ones. And this step has some similarities with the feature selection step Clara has told us. But the idea is different, since in this case we're searching for a subset of confounded candidates. So the obvious question is why you do this step instead of throwing all your data set into a causal discovery algorithm and get the confounders from there. So there are two reasons. The first one is that we've tried to do so with many different algorithms and open source packages. And in most cases, they either run out of memory with 400 features, or they last 20 or 25 hours to provide us results. And second, in the few cases we managed to get these results, we had to analyze 400 nodes and all the connections, so it was almost impossible to see if the graph has any business sense or to validate all the edges. So given these two problems, we thought it was a good idea to first reduce this subset of features and then try some causal discovery. And that's our next step. We ran 3 methods in parallel, and we combined all the results in one single graph. And then we apply domain knowledge. We redirect some edges, remove some others, or even force some connections in the algorithm priors that we know they are happening in the real data generation process. And once we have our graph, we are ready to transform our causal effect estimation problem into a statistical estimate. We do so by, obviously, looking at the graph and getting the variables we need to control for, also known as the adjustment set. Then we're ready to estimate the causal effect. And here it's very important to remark that not all estimation methods are suitable for our case. Why? Because we have a continuous treatment. And most well-known estimation methods are more oriented towards binary or multi-class treatments. So in practice, we tried as many methods as possible, but we've just selected 3 of them for this presentation, which are backdoor regression, an S-learner, and inverse probability treatment. Then we apply as many refutation techniques as possible, but to check the robustness of our estimations and see the sensibility. But again, for simplicity, we will just discuss 3 of them today. And finally, we've come this far to make the best possible decisions. In our case, these are personalized decisions, as we want to get the optimal discount for each customer. So we generate counterfactors with our causal model, and then we apply a cost function to see the optimal discount for each case. So now I'm going to explain some of these steps with more detail. In this case, I will focus on the dimensionality reduction block, as just mentioned. So the first question to ask here is what kind of variables we aim to select under a causal ML perspective. We're looking for confounders. And a confounder, as you know, is a variable that influences both the treatment and the outcome. So they must be included into the adjustment set if we want an unbiased estimation. But why only confounders and not other kind of features as strong predictors of the treatment or mediator variables? Basically because we will be adding high variance and selection bias to our estimates. Mateus, who has given a talk on Stream 1, has a lot of work on this field, like with many examples demonstrating that only strong predictors of the outcome and confounders should be added to the adjustment set. So I take this opportunity to thank Mateo for his work, because it has saved us a lot of time. Okay, now how do we go from 400 features to 20 features to a reduced subset of confounded candidates? We do it in 3 steps. First, we define a model where we regress the outcome against the treatment and the covariates, just as in the predictive ML approach. We apply the same technique for feature selection with 2 differences. The first one is that we force the treatment not to be removed at any feature selection iteration. And why so? Because we know that the treatment is a strong predictor, is a weak predictor of the outcome in this case. So it would be removed, as we've seen. And second, because we know there are some variables that gain predictive power when interacting with the treatment. So if the treatment is removed, these variables will also be removed. Second step, we do the same, trying and regressing the treatment against the covariate, and we got another subset. And the third step is just to join both subsets in a final candidates selection. And with these 3 steps, we go from 400 features to 20 features. This means that the majority of our data set was noisy, and so it made sense to us. And then we ran 3 causal discovery algorithms, Peter Clark's fast causal inference, and Lingam. And as I said, we combine the results and we apply some domain knowledge. And then we apply backdoor criterion to get the variables we need to control for. And that's how we get to this graph. This is a summarized version, as there are some features that only influence the treatment or only influence the outcome that we are not displaying here. There are just 5 confounders. And here, one of the most surprising results is that just 2 of these out-confounders were selected under the ML approach. So we were not controlling for the right variables under the ML approach, predictive ML approach, sorry. Then before looking at the estimation results, we want to look at the confounders distribution. What we've done is to split our confounders in different stratas and look at the treatment and outcome distribution for each strata. In this case, we have the stratas on the x-axis and the treatment distribution on the y-axis. And we can see, for example, this variable, loss percentage estimation, it represents a pre-calculated percentage of the unpaid debt amount over the total debt amount of past customers. So, for example, a value of 80% means that similar customers to the current customer lost the 80% of the debt when they were in default. If we take, for example, in this case, values between 90% of loss percentage estimation and 100, which is a lot of unpaid amount, we can see that the discount values are higher than if we look at the values below 90%. This is intuitive, as our advisors are looking at this variable to give the discount. The same happens with the number of years in default. The higher the number of years in default, the higher the discount given. So this is a confirmation of the non-random allocation of the treatment, as we can clearly check that our financial advisors are driven by these features. But to confirm if they are also a source of confounding bias, we must look at the outcome distribution. So that's what we do here. We control for some treatment levels, and if we look again at the loss percentage estimation, we can see that the higher the loss percentage estimation, the lower the success rate. So this is also intuitive, and the higher the number of years in default, also the lower the success rates. So now that we have our adjustment set, we are ready to estimate the causal effect. We apply the 3 methods I've mentioned before: backdoor regression, S-learner, and inverse probability treatment weighting. And we have the dose response curve, which is the same as the effect curve Clara showed you, and the marginal dose response curve, which would mean the effect under a continuous treatment. So the most important result here is that under the 3 methods, we see a positive effect of increasing the levels of discount on the probability of success. This is intuitive and aligned with the domain expertise on the ground, and it contrasts with the flat effect we saw under the predictive ML approach. Then, once we've got our 3 estimates, we want to evaluate them. What we do is to apply some refutation methods to check, to validate these estimates and check for the robustness and see which one of these 3 is more reliable. Here we use a simple technique that is placebo treatment replacement. We replace the real treatment with a random treatment that follows the same distribution. We re-estimate the effects, and the desired result is that it goes to 0, and that's what happens. So good news. Next one is random common cause. We add random variables to our adjustment set. We re-estimate the effect, and it should keep the same, and that's what happens. So this is good news. And finally, we do some sensitivity analysis. We use the values to quantify how strong an unmeasured confounder should be to neutralize the estimated causal effect. So our results show that the potential unmeasured confounder should increase the likelihood of both the treatment and the outcome by 31% to neutralize the effect. So this gives us like some proof that our estimation is robust, as no other confounders has such an association with our treatment or our outcome. And given all these refutation results, we choose backdoor regression as our model because it has a greater e-value, and it was the one who has a flattest marginal effect. And now Clara is going to explain how we use counterfactuals.
So once we have a causal method, which is of our preference, we want to get to that percentage that can be personalized for each client. And here we have calculated counterfactuals for 2 clients that are very different. So these are the variables, the confounding variables. So the first customer has been in default around 4 months. He has been, or they have been in the bank for 5 years, and the total debt amount is very low, 400 euros. The percentage of discount was 38%, and he actually, or they actually could pay after this solution was offered. If we go to the curves, the green point represents the percentage of discount offered to this client, and the causal dose response curve for this individual shows us that if the percentage of discount had been a little lower, the probability of success wouldn't have changed that much. The second customer, though, their state or financial state is much more deteriorated. They have been in default for 11 years and in the bank for 15 years. And the debt is quite higher, $83,000 or euros, sorry. And the percentage of discount was 71%. If we look at the curve, we can see the red dot, which represents the discount offered in reality or in the past. If we look at a lower percentage of discount, we see that the success, the probability of success is lower. But also, if we move to the other end, to higher percentage of discount, the probability of success doesn't increase that much. So these type of results are very insightful and can be used in two ways. First, to give this information to financial advisors so they can better decide what is the solution or the percentage that they would like to offer with these counterfactuals, and also these values of these curves can be used in a cost function to compute the percentage per client. I think we're running out of time, so I'm going to be quickly here. So we're wrapping up, and for us, moving from predictive ML to causal ML have had the three main advantages. We have addressed confounding bias, we have started to understand the effect of treatment on outcome, and found causal variables for business insights. So now with those confounding variables, also business and financial advisors can also tailor solutions, and we have built counterfactuals to optimize the percentage of discount for these offers. And so here we have also a table of comparison, and the one thing that was better predictive ML was in accurate predictions. So as we said, this is not so important now in this problem, because we want to make like sound decisions. And just to wrap up our lessons learned, we have found that causal ML has actually helped us to solve the problem where solely predictive ML approaches couldn't solve it. We have invested, as Javi said, a lot of time in causal discovery, along with talking with business experts in coming up to those confounding variables. Most of the known estimation methods are more oriented to binary treatment, and we had a continuous treatment, so there is still a line of research and work to be done there. Explainability, which is something that causal ML is good at, it's very important for us because of the highly regulated industry, and also because explainability is good anyway for customers and financial advisors as well. And lastly, like a cultural conclusion, which is comparing these two approaches have helped us introduce causal ML into the company, because we were more used to predictive ML, but by this comparison, we can see the advantages. So thank you very much.
Amazing. Thank you both. We do have a couple of questions, if that's okay. First one, are you reducing the features using a lasso regression in steps 1 and 2?
No. We're using an in-house methodology that combines permutation feature importance and recursive feature elimination. It's iteratively. So we rank the features first, and we try to remove subset of futures iteratively.
Amazing, thank you. Second question and final question. In your predictive ML model, do you treat the treatment variable in the same way as other features?
No. In the predictive, you mean the predictive ML approach? Yeah. No. Yeah, we treat it the same way. So it's removed and we add it at the end because otherwise we wouldn't be able to do interventions or estimate the effect. But yes, it's like in the first step, it's the same as other features.
So we included as in both approaches the treatment as a percentage.
Amazing. Clara, Javier, thank you very much.
Thank you.
Okay, that's a wrap for stream 2. Thank you to everyone who came, and especially thank you to our speakers. We really appreciate you. We'll take a 30-minute coffee break now, and then after that, stream 1 is continuing. We have talks. We have 2 talks. The first one is Causal Modeling for Social Causes by McCann, and the second one is Causality Upside Down by Alex Molak. So we'll see you there. Thank you.